Hello and good evening, everyone. Welcome to the event. It's a collaborative event between TensorFlow User Group Mysuru and Must Research. TensorFlow User Group Mysuru is the leading TensorFlow chapter in India. Must Research is dedicated to promote excellence and competence in the field of data science, cognitive computing, AI, ML, advanced analytics for the benefit of the society. Ms. Usha Rangaraju is the chapter lead of TFUG Mysuru, GDG, Vimal DS. Ms. Usha Rangaraju is also India's first female Kaggle Grandmaster. You can follow ma'am on her social handles like Twitter and LinkedIn, links given in the description. This is our core team. It's a collaborative efforts of these peoples so that we are able to bring a successful event every week. We are a team of common to three communities: GDG Mysuru, TFUG Mysuru, and Vimal DS Mysuru. Due to the hard work of these members, we were able to achieve the top community for TFUG in India. This is our social media team who has put in their hard work to reach out the event to wide range of audiences. You can follow our social handles for upcoming events and the updates. We are trying to pull out each event. We are trying to pull out more than 2 events each week. These are our community partners. Co-Learning Launch is an online platform for data science, and they also provide resources which you can use. Applied Singularity is also a data science resource where they also have an app you can download and use it. Confab is an online platform to conduct online conferences. So without a further ado, we'll get started with the session. I invite my co-anchor Prithvi to give an introduction to the first anchor.
A very good evening, everyone. This is Prithvi speaking, and the first speaker for today will be Joy Mustafi. And the topic he's going to be speaking about is applications of artificial intelligence research. So he's basically the chief scientist at Aviso Artificial Intelligence, founder and president at Must Research. Over to you, sir.
Thank you. Hello, everyone. Good evening. Let me just share my screen. Can everyone see my screen?
Yes, sir.
Just a minute. Why it is not coming full screen? Okay. Hello. So I'm Joy, and I'm currently working with Aviso as chief scientist, as well as we at this Must Research, which is a non-profit organization to democratize AI across the nation. So, and today I will be speaking about the AI research applications. So some of the interesting project, like from my journey, I will mention a few interesting and really challenging projects where we have to really think like out of the box and then solve those problems. And so I have around 18 years of experience now, and all through this artificial intelligence and data science domain. So I started my journey in 2002 when I was a researcher at Indian Statistical Institute. And I started my first program also on neural network, and that too written in C. So C programming language was that time very popular, and there was no Python and a few other like R, those kind of scripting languages. There was no inbuilt libraries also available. So we used to work like everything from scratch, right? For an example, like the neural network which I wrote that time without having any package like TensorFlow and other, right? I mean, the deep learning packages and all. So it was like a backpropagation algorithm with two hidden layers, and then like it's a multi-class classification. But what I was trying to say is like, although we have a lot of things now within the community, probably we are exploring multiple things. We are like getting online data and so on, right? But sometimes when you go inside the algorithm, like what is exactly I mean by that, or how the mathematics and statistics behind it, what is the computer science or computer science engineering behind it, right? So all these things are very important once you have to do some research and then come up with a better idea, better algorithm, and so on, right? So the novelty on whatever we are doing to come up with the new things is always better to understand the existing algorithms and all the formula in details, and then come up with the new things. Again, for an example, like I have around 50 plus patents now, and all those patents are with the new ideas. You can just search my name in Google, like search Joy Mustafi plus patents. You will get a list of all the patents. So what I will do quickly cover, like, first of all, what is AI, right? It's not new for you. All of you are members of TFUG or somewhat related to the data science community, right? Or members of MUST. So AI is not new for you, and AI is also not new for the community. Although in the corporate world, recently we had like lot of like discussions and overhype, right? I mean, a bubble created across the corporate world, like, okay, we need to apply AI in somewhere, somewhat, right? If it even if it is a small regression line, they're saying like it's AI, or it's just a few if then else. Many people are saying it is AI, or some automation, they are mentioning it AI. But it just happened in last 2 3 years, those kind of boom. But the AI, or artificial intelligence, first coined, that particular phrase was coined by Professor John McCarthy and team in late 50s, in 1956, in a conference, when they came up with that, look, okay, in the normal biological neuron, how it works and how a computer can actually simulate that, right? And there are a few examples also, the old examples, like learning Chinese checker strategy, playing chess, right? For an example, IBM Deep Blue, it was like late 90s, not too old, not too new as well, but it defeated Gary Kasparov, and there is no machine learning algorithm inside IBM Deep Blue. It all had is like a complete set of all possible chess moves. So these are actually all the kind of moves, and it is stored in a proper graph database, so that before Kasparov thinks, the Deep Blue can think faster, and then I mean, defeat the human being. So that was like few examples, but IBM didn't do any business with Deep Blue, right? But when the Watson came, that time, like IBM Watson was actually then again being transformed for industrial purpose, like in different domains, like Watson for healthcare, Watson for finance, right? And that way, like the other companies like Google, Microsoft, Amazon, everyone started putting like real AI in their multiple applications, right? Even now we have the open source libraries distributed by some of the corporates, as well as some of the open source communities as well. So from that era till now, right, we have enhanced many things. So from late 50s to till 2020, even for last 2 years, we have actually enhanced a lot of things, including the deep learning and all, right? But whenever we talk about all these, right, most important part is actually the data, what we get and how we collect data, from where we should get the data. So data can be also different types, like structured, unstructured, semi-structured. And typically for like AI practitioners, our expectation is, including inside the office, oh, someone will give us a beautiful plethora of data, and they will just request us, can you please fit a model? But that's not reality, right? In industry, in academia also, right? We need to collect data accordingly. Even from a customer, if I ask customer like, okay, can you please give us data, and we will fit a model. So that's not the end of the conversation, because then they will ask like, what kind of data? Then probably we say like, okay, can you give us like tabular data for your last 5 years transaction? Then they will say like, okay, how many columns you want? Okay, I need like this variable, but those variables are not my x1, x2, x3 for my machine learning model. Then I have to do a lot of variable transformation. Then they will ask like, what is the volume, how many records you want, what is the time frame you're looking for? So it's not like they have a Kaggle challenge in hand and just push like, okay, download this CSV file and start putting your deep learning or traditional machine learning algorithm and show us the result. Because then they can also do it, right? They won't hire any data scientist, or they won't sign any contract with the AI product company or a solution company. So that's the challenge. Then once we have like, okay, structured data like a tabular data, but it's a huge like in volume. It can be semi-structured data like log files, IoT signals, like a lot of different kind of semi-structured inputs. It can be like a document table, which is like a table but not in a RDBMS format. It can be unstructured data, totally like free text, image, audio, video. And we have now this YOLO kind of framework, like everyone is putting a camera and putting like YOLO behind and saying like, okay, I'm having like live image, live object detection and so on, right? But my suggestion is like, please go through that YOLO code and learn first that like how it is happening. Because tomorrow, if it is like specialized for one particular domain, if I want to use a kind of YOLO kind of architecture in healthcare domain to identify like some inside the body to identify a tumor, or think about like a biopsy test, and with that camera can I use computer vision, or think about like cancer cell, or even this coronavirus, like gene structure of coronavirus, if I want to explain like on a time series image, like how it is actually uh, I mean distributing, like so it's reproducing, or the virus is actually spreading. So from the gene structure and the like the protein and all those things through image, right, through other structured and unstructured. And then these are not separate projects, because I have seen like a lot of projects where all these things are combined together. So we have text, we have image, we have structured data, we have semi-structured data, and then we are combining, we have also audio and video, and then combining all together to have like a decision which will have these parameters, or we say like these are the features we focus on the or measure the innovativeness in, especially in must research, right? So definitely I'm not going to explain the left side diagram. All of you are familiar with this, like the biological neuron and how we are putting like the activation function, and then the neural network is being built, and all of us are familiar, at least in 2020. But what I want to say here, like all the 4 points written, like the adaptiveness, so how the information changes, and then the algorithm or the system can change accordingly, right, to resolve the ambiguity and tolerate the unpredictability, right? For example, like the normal classification algorithm or a time series analysis will fail in this COVID situation, right? Because the normal time series analysis will actually get like last 5 years or 10 years of data. But then in 2019, in July, COVID was not there. In 2018, July, the COVID was not there. If I am capturing monthly data, right, so that time series analysis will fail. So it is not adaptive. Then interactive, right? So when we are getting like human input also in between, right, a little bit of like reinforcement learning concept, but not totally on that. It can be more with respect to reinforcement learning. Then iterative and stateful. The decision may change, right? We sometimes we have like, okay, this is my decision now. I want to turn on the AC, and after 5 minutes I am feeling cold. Then I want to like increase the temperature. Then again I am feeling like again not comfortable. Then probably I will turn off the AC. So now the AC must be turned on for an hour if the decision I have taken at the beginning of the night, versus the decision changed over time, over state, and lot of different parameters which actually drove me to change the decision. So that's very important. Then the contextual part, right? The lot of things like we are talking about NLP and automatic Twitter handle. We'll get like a lot of Twitter dump, and then we'll analyze, right? But first of all, like what is the context? That's very important, because if it is specific to any particular domain, right, the discussion will vary. For an example, like the word operation in healthcare domain, it is like related to anatomy. If it is in military, right, then it will be some war, for an example, like Operation Kargil. And if it is in mathematics, then it can be Operation Research. If it is in IT, it can be IT operation. So a lot of things. I mean, the same word can have like different meanings. And that is very important because the algorithm also changes, right? The same architecture which we build for, like suppose healthcare, will not work on any other domain. For an example, suppose on finance. So they may vary because of the volume of data and so on. So I'll just highlight few of the projects here. For an example, the first one, like Adam had 5 apples. He gave 3 to Eve, and how many are left? So this is the kind of like a problem, like an arithmetic problem of standard 2 CBSE student, and how a computer can solve this. Okay, so that was the challenge. Okay, so this actually was my first patent. So if I now go like through the computer, how it will understand. So Adam is nothing but a proper noun, then 5 is a cardinal number, then apples is the plural of a common noun. So and we are actually storing this number in an accumulator, and then the next sentence is he gave 3 to Eve. So who is he here? It's a pronoun, but we are trying to connect that with the noun Adam. Then 3, we are again converting that 3 to actually digit 3. The word apples is missing, but we are assuming like this apples is actually from the first sentence. So it's called ellipsis. The first one is anaphora resolution. So Adam and he connected, and then this apples and blank is connected. So Eve is another object here, indirect object. And the last sentence is very ambiguous, like how many are left. But all of us assumed the question is how many apples are left with Adam, because the problem statement started with Adam here, and the transaction also started here, and the operation is in the second sentence. So these are all the things which happen inside our brain, but it is not written in natural language also, and so it's very difficult for a computer to understand unless and until we apply all these like anaphora resolution, ellipses, right? So the disambiguation, all these things in the steps, and then finally we are computing. But you may think like why Joy invented this system, and he also mentioned like it's his first patent, right? I mean, what the damn good thing here, right? Why we should go for a patent on this? It's a very simple kind of problem, right? So we can anyway solve it within 2 seconds or 1 second. But if you see the left side problem, that one 6.8 kg toboggan is kicked on a frozen pond. It acquires a speed of 1.9 meter per second. The coefficient of friction between the pond and the toboggan is 0.13. Determine the distance which the toboggan travels before coming to rest. Well, I'm not going to ask you the answer here, but I think all of you will agree like this is a difficult problem compared to this Adam, Eve, and Apple. Why? Because this has like first of all, like this toboggan, the word is unfamiliar. It's not in our dictionary or in our like daily you may know this meaning, but when I heard this problem, I found like, okay, I don't know the meaning of toboggan, and it's not familiar like Apple. And second is like the coefficient of friction and all. Oh, I forgot because I studied those in my 10th standard or 11th standard, but now I forgot, right? So those are the things like why we try to avoid and say like, okay, this is a hard math or hard problem. But the thing is like, this is not hard problem from mathematics or physics perspective. It is hard with respect to English perspective. So next, not only the text, like text plus image, like as I mentioned, like, I mean, it can come all together. So text plus chart or table, like, and then, so this data interpretation. So you have to measure the, actually the table here, or the chart here is totally an image, right? It doesn't have the origin of the table from where it is generated. So if you see this particular 1997, this particular column, right, and it is showing here in between 40 and 50. So if I run OCR, definitely I can get like this 0, 10, 20, 30, 40, 50. But in between 40 and 50, that means it is 45. And that value is not, I cannot get through OCR. So I have to mix them with image processing as well as some like this through this geometrical figure to count the pixel and compare with the scale, which is in the left side, and then compute that. And also compare a lot of things, get the information from the text portion above and the question which is asked below. So again, there are the 3 segments which we can solve. Similarly, it can be a table, but this table is also not a traditional RDBMS table. You can see like it's a multi-header, right? So year and then the year itself. Then there are 2 sub-columns like applied versus qualified. Then there's some numbers, then state. So all these things are like, this is my second patent actually. So again, you can search with my name and this kind of queries and get more details on these patterns, like how I solve. So next is like not only that, like some puzzles, like for an example, Sudoku puzzle solving and all. So these are like all R&D projects in Mast. Again, you may think like why we are solving Sudoku puzzle. The thing is like the same architecture can be used for any other. Like it can be used for MIs there in banking. It can be used for number plate detection. It can be used for any other, like detect mobile number from a poster or a visiting card and store it in a corn. So in your contact, if it is directly stored when you're taking a photograph through your mobile of a hoarding or a small advertisement on in a billboard, right? And so the same algorithm can be applied here. But what I want to say here, like in the Sudoku, the digit recognition, we used multi-class classification. It is 9-class classification. There is no zero in Sudoku, right? But to solve the Sudoku puzzle, we haven't applied machine learning. It is definitely AI, but not machine learning, because machine learning is subset of artificial intelligence and deep learning is subset of machine learning, right? So deep learning, when we have like at least more than two hidden layers, then we call it like a deep. We also built some robots. I think Swayam will also cover a few of the things. He's as a speaker today, and but these things are again the hybrid kind of AI applications where we are applying like speech plus vision plus like image, sorry, text, normal text, and definitely other inputs, like even including the sensor inputs, right? What we are getting like from a distance sensor, like ultrasonic sensors and all. So combining all these, right, so we are actually able to create this community. So what is the objective of Must is mainly to make like intelligent India. For an example, the Make in India and Skill India and Digital India initiative, right? We are coming up with, right now we have around exactly 501 data scientists in Must research. So 501 data scientists, all of us are working in different companies or studying in different universities, but we are all coming together in a real community where it is not like we are connected over online and all. We also meet in person. A lot of conference and workshops we arrange. Right now, today also we are having it with TFUG. We collaborate with multiple other organizations and try to democratize AI to make like our nation be on the top on this particular field. So I want to quickly show a demo if I have like a few more minutes. So this is the first robot we made. Even Swayam, he actually made this, who is one of the speakers. And can you hear the sound? I think it is audible, right? So this particular robot is mainly on a speech-based. So it can identify the speech and like speech to text, and then text to command, and then it acts based on that command. And the second robot I want to again show, this Softy. It is so Mask Research in collaboration with Microsoft Garage. We made this particular robot where Microsoft Garage sponsored the hardware as well. And this is a combination of multiple things, not only speech. It has like speech plus vision and text and other signals, everything. Okay, so here what Softy asked, first, like she took the photograph of the user and then said like, I see a female of age 21. So that means she first identified like, hi, hello Aditi, how are you? So that means it identified the person, identified gender, identified age, and then identified emotion. And that's why it said like, you don't seem to be smiling. And then with the sensor, get it and how far it is, and then it put like the high five.
Can you read this text for me?
Now it is applying OCR to read the text. So she will hold a paper where it is a printed text.
Can you read this text for me?
So on the fly, there is like with interest of, so you can say like ask for something, it will search. So for the interest of time, I'm just forwarding it to for the, okay. So
It's in the fridge.
so she is giving a message. Sorry, yeah.
Food is in the fridge.
So Aditi told like a message for Dolly, another person, and the message was food is in the fridge. Okay.
Bye, Sophie.
Yeah, so the interesting part here, the data privacy and other concern, right? So Aditi gave a message for Dolly to Softy, right? And Softy, once she I mean looked at Dolly and then identified the person, and then only gave the message like the food is in the fridge only to Dolly. Even before, suppose in between Aditi and Dolly someone else comes, and then Softy will not say that message. So this is also like we have taken care about the data privacy. Now it's a complete like a package, like where we have like lot of applications like NLP, speech, vision, sensors, robotics, right? And just think out of the box. That is my suggestion. Like and how we can actually make ourselves brilliant with respect to this, the data science and AI things, right? So and this is for Must Academy. We recently launched a program. It's a completely application oriented like data science certification through Must with a very affordable course fee. You can visit the site academy.must.co.in, or you can search Must Research Academy or Must Academy as well in Google to get, and connect me over LinkedIn. I am available and very open-minded to discuss anything on today's lecture, as well as any other comment if you have, or if you want to just discuss about career, right, what to do next and all. Please feel free to connect me over LinkedIn. Just put a message like while connecting, like you attended my session in TFUG, so I can easily get the connection. And then these are the focus area what we are actually covering in the Must Research Academy, mostly like the, it's completely research driven, right? So research driven is very important, right? It's not like, okay, you're just learning through some theory, and I am learning linear algebra, then probably eigenvalue, eigenvector, but I didn't know where I have to apply eigenvalue and eigenvector. Or I'm applying, like I'm studying probability, and then tossing a coin, but I don't know where to apply probability in my day-to-day life, because in my office I will not coin a toss. In my office I will not throw a dice to get a probability, right? So I have to apply something, but to know where it is being applied. So that's very important. And so education, then experience, like the through the project, and that project is also very hard project. So in our like in Must Academy, so it's actually surrounded by all these 501 data scientists, right? So it's a community driven. So definitely it's not so easy, like, okay, we can just show some Titanic problem and a logistic regression and come up with the result. That is not feasible here. So it's all hard problems, and but learning for like something which is totally novel, and definitely to enhance the career in such a way like we can differentiate ourselves from rest of the world. And definitely the exposure of this, like publications, so we always prefer like publications and like patenting, right? So protecting your IP. So yeah, so that's all from my end. I think I'm well within the time. Should we go for a few questions now, or I can just minimize my screen and check, like, or we can take it offline, whatever. The organization, I mean, hello?
Yes, sir. As of now, I look like the audience don't have any questions. They're pretty satisfied with what you have thought, and we would like to thank you for sparing your time and enlightening us on applications of artificial intelligence. We'll wait for a few more minutes if there are any
Sure, sure.
doubts.
Absolutely. So let me know when I should stop sharing, and you can switch to next speaker.
Okay, sir. I don't think there are much questions. If at all the audience have any questions, you can ask sir on his social media handles. And yes, sir, I thank you once again for
Yeah,
spending some time with us and like enlightening us on applications of artificial intelligence. And yeah, all of the audience can get back to sir on his social media handles. Thank you, sir.
absolutely. So I'm very much available on LinkedIn. That's my, I mean, I am regular on LinkedIn. So please just search my name, Joy Mustafi, in LinkedIn. You'll get, and this just connect with me and put a message like you attended into FUG in master session, so we can easily recognize each other, and we'll start connecting. And please
Also,
explore this Master Academy as well if you want. Yeah,
there's this one question. I'm
sure.
just popping it on the screen.
Okay, let me minimize. What is this
I've just
question?
popped it on. Okay. No, the question
Uh,
says, can you please
okay,
give some
comment,
information
comment.
about robo
Can't,
hardware?
which one? Can't think of the right questions.
So about that, I popped it
Okay,
on the
robo
screen.
hardware.
Can you
Okay, okay,
please
okay.
give?
Okay, so I got. Acha, acha, there are a few other questions as well. Okay, robo hardware. We used like two brains, right brain and left brain for Raspberry Pi and Arduino Uno. So wherever we are applying the AI algorithms, we use Raspberry Pi, and there are few things which are like very much straightforward decision, right? For an example, like that high five and all those things, we used Arduino Uno, like just like if then else kind of condition. But where there is like a fuzzy logic or being I mean instrumented through the machine learning, we used Raspberry Pi.
Okay,
Okay,
sir.
there was another question
There's
on
an
the
other.
eligibility
Yes, sir.
criteria. No, there is no eligibility criteria. It's all about your interest in data science. That's it. No other criteria like you have to know data science earlier or mathematics, statistics, or probability. Nothing is required. So we start from scratch. Anything else?
No, sir, there's another question that I popped on the screen. How to file a patent? Is that a simple procedure or how?
Okay, patent is not so simple. Definitely, there are a lot of things, so we can definitely discuss offline. I mean, just connect me over LinkedIn, and you can just search my name, so Joy Mustafi plus patents, and see like all the patents are related to one organization as well, right? So I had like 30 patents, more than 30 with IBM, then two with Microsoft, then 8 plus with Salesforce, and recently started with Aviso as well. So all these patents are like not only my patent, so it's a like organization plus the inventor kind of thing, but it has a procedure. It's not like just go and find a patent, right? For same for publication also,
Yes,
definitely your idea
sir.
has to be very much novel. Yeah,
Due to the constraints, the other questions you can ask
yeah,
sir
yeah,
on
we can just
his LinkedIn handle.
hmm.
Yes, sir.
Okay, I think
Thank you,
these
sir.
are all done. So last question, what kind of jobs? This is a very generic, and I don't think it's a correct question. It won't replace any job actually. So I mean, definitely it will create a lot of new jobs for AI scientists and data scientists, right? It will not replace like, so the human invention, the wheel, right? It was not replacing legs, but just to like minimize our effort. So all the inventions are like that, not creating jobs. Okay, thank you so much. So, and then let's take the other questions offline. Thanks a lot.
Yes, sir. Thank you, sir. Now, let's welcome our second speaker to the event, Swayam sir. He is a senior data scientist at Indegene, and he'll be speaking on the topic of deep learning techniques for NLP in healthcare.
Hello. Hey, hi. Thanks for the introduction. Let me share my screen. Okay. I hope my screen is visible. Yes, sir. It's
Yes,
visible.
sir. Yes, sir.
Okay, perfect. Great. Thanks. Thanks. Hello, all. A very good evening, and thanks for joining us for today's event. In this session, we'll talk about deep learning techniques for NLP in healthcare. Myself, Swayam, I work as a senior data scientist at Indegene. I have 4+ years of experience in data science, and I did my post graduation from Oxford University in 2018. And I'm also a machine learning mentor and deep learning.ai ambassador. I also love making intelligent and autonomous robots. And very recently, we made a COVID robot for Chennai Police to monitor the contaminated zones, right? And apart from this, I'm also a Must member. Must is a very interesting platform where we collaborate with fellow Mustans, and we work on interesting ideas. We work cool projects, and simultaneously in the process, we learn building and developing our knowledge. So if you are interested in joining Must, you can visit the website. So the agenda for today's session is we'll start with discussing on the importance of NLP in healthcare. Then we'll talk about and look into the task-specific NLP use cases and how do we address and solve them. And then we'll conclude by discussing what are the implementation challenges and how do we overcome them, right? So let's start with the first question. What is the need for AI in healthcare? So over the years, we have seen researchers proven AI-driven techniques to effectively solve a specific healthcare problems, right? So as you can see in the image right-hand side here, after the 2015 ImageNet movement, deep learning techniques were very regressively used for the computer vision task in order to accurately diagnose and detect a medical condition, right? So as you must have been seeing in this current COVID situation also, there has been lots of research being going on in developing a product. So X-ray can be used in order to diagnose COVID positive or not, right? So that's where you see that these applications are very effective for a doctor to take a necessary and quick decisions. Okay, so the type of data what we are talking about here is on NLP, which is specific to healthcare. So the type of data varies from structured to unstructured. You can consider an example, a tabular data with all your medical conditions, ICD codes, and you have a significant value associated to that. So the tabular data can be a structured data, and any form data where you have your rows and categories to an extent can be semi-structured, and rest all kinds of text which are like your phrases, paragraphs, and documents falls under unstructured. And with such vast amount of data, the typical applications in healthcare, the typical applications you can see in your screen. So we summarize lengthy blocks of narrative text. So, and ideally a typical application is that lots of documents are being written by a domain expert. And that's where you will see that they will write the terms which are not so much easy to understand for a layman person, right? So there is a conversion involved in terms of writing a same sentence with the other representation. Say, for example, a simple sentence will be, I have renal impairment. And you rephrase and summarize that I am suffering from a kidney failure, right? So these jargons and negations are being captured using these NLP techniques. And we also, a very similar and common problem statement is converting our unstructured data to a structured data for mapping the key components within an EHR fields, right? And also you can do a common query question and answering system which require reference to a document, and you can get your retrieval possible answers. So on the screen below on the image, you can see the range of applications varying from research till analytical reporting, right? And today we will focus on predictive analytics and adverse event detection. Considering the core application in this domain are like representation learning, representing your context into the vectors which are efficient for learning the model for a downstream task, and common downstream tasks like information extraction and clinical prediction. Right. So considering that, let's start with our first use case. So what is adverse event detection? Let's understand by looking at the example here. So the example says that had headache, took crocin, got vomiting. So given the statement for detecting an adverse event means that we need to identify the undesirable effect a patient has faced during the medication period. Okay, so let me explain how do we solve it, and gradually you will understand better what it is. So given this statement, what we do for adverse event detection, we first build a NER model. So given this statement, we feed this input to the NER model and we'll extract the entities. So the entities present here is crocin as in drug, and headache and and vomiting as a medical condition, right? So you have two entities available, and then what we do, we make a possible combinations of drug and medical condition. So for this case, we have two pairs, right? One is a crocin vomiting, another is crocin headache. Then what we do, we feed these pairs to a relation extraction model, where the inputs will be these individual pairs, and then we'll predict that given the crocin, the relation with the medical condition of vomiting is adverse event. Means that a person taking crocin should not get vomiting. On the other side, the relation between crocin and headache is of indication. Means a person takes a crocin when he has a headache, right? So any undesirable effect with respect to a medication is considered as an adverse event. So the adverse event task is a natural language understanding task, where you can imagine it breaking into various subtasks. Various subtasks like sentiment analysis, name entity recognition, and relation abstraction. And the typically data sources for these AE detection are like unstructured clinical notes and social media posts. Okay, so the first step is to build a sentiment analyzer. So sentiment analyzers helps us to classify whether the given statement or a context has an AE or not. Okay, so to do so, what we do, we take our input sentence, we feed it to the embedding layer, where we convert our sentence into the vector representation, and then pass it to an encoder. It may be either CNN or LSTM to learn the feature representation and encode it into a fixed lower dimension space. And then we pass this learned features to a dense layer, softmax dense layer for classifying. So it tells us, okay, given this statement, whether it's an AE or it has a non-AE. Then we further, as we know that this is a very baseline model for the first attempt what you get, and it's always it's recommended we optimize our model by various techniques. So here let's consider optimizing your model with hyperparameter in order to improve your baseline performance. So consider the simple techniques, like you will look into the various consideration of features, whether to look into the stop words, punctuation numbers, what the importance are, then varying the number of layers and hidden layers, and then working out with different dropout layers and learning rates, and so on. So these parameters will ideally, you'll see, end up varying a delta change in your final accuracy, and helps to get improved in the baseline model. Then talking about the embeddings plays a key role in representing the context. So over the time, we have seen that embeddings have evolved from static word embeddings, which were like, you can understand, right? A word-to-vec based skip grammar continuous bag of words model has been till now transformed at today's date to a contextualized word embedding. So contextualized word embedding, as the name suggests, right? So the vectors is dependent on context, and very prominently we use BERT, Elmo, and ULMH fit for the different representations. So ideally, we evaluate these vectors based on two criteria. One is the intrinsic measure. So we look into the similarity between the two concepts, how well it is capturing. Let's suppose consider kidney failure and renal impairment, right? So if you look into these two concepts, they both look have a different lexicon properties, but they both are semantically same, right? So an ideally a good word embedding which has learned the representation well should capture the semantics. It should say that both the context concepts are same, right? And we also evaluate the embeddings with a downstream task, where we pass those embeddings to our fully connected layer, or LSTM or CNN, for encoding the information into learning the features, and then seeing how well we improve the downstream tasks like classification, NER, and so on, right? So the one important and key thing to notice here is that it all depends on the representation what you are feeding. So if you feed a good representation to a simple model, you will see a better performance compared to feeding a poor representation to a complex model, right? So a complex model may be a large model with more number of layers and lots of hyperparameters, right? So the representation plays a key role. Now, considering our use case of identifying the AE, so what we do, we need to train our NER relation extraction model, right? And we do so by training both the models jointly in an end-to-end fashion. So if you observe the picture, this diagram here, so what we do, we take our input sentence, say for example, had headache to crocin got vomiting, right? So we take this input and we transform it into a CONL format. right? It's a format where we take the beginning, it's the outside, it's the inside. So we transform it into CONL format and feed it to a BERT model. So from the BERT model, we'll extract the attention weights of the features, and we pass this to the feed forward layer, where we have a softmax on top to classify and identify the entities. So this NER model will give you the probability of the final output that this is a word, this token belongs to drug with this probability likelihood, and this token belongs to your conditions with this likelihood. Then what you do, we create an incremental pairs of drugs and conditions, and we feed it to another model, which is a stack. It's an end-to-end stack model, right? So in a back propagation, both are learned together. So we pass the NER paired output to a word embedding first, and then we also concatenate our attention embedding from the NER model in order to incorporate the NER features as well, right? So ideally, with traditional techniques, you will see that we would train NER and RE models separately, which creates a gap as the features learned from the one model is not carried forward to the other, right? So these end-to-end model address those tasks, and we concatenate the attention vectors to the embedding layers and feed it, pass it through the FFN layer. So here, if you see, we have two FFN layers. We have feed forward head and feed forward tail. It's nothing but FFN feed forward head is for FFN layer for your drug entities, and feed forward tail is for your condition entities. So we feed our vector representation to which has a shared weights, right? So these FFN layers carry a shared weights, and we pass it through a bi-affine classifier. So bi-affine classifier helps us to model the binary relationships between two concepts or entities. And in general, if you try to understand, bi-affine classifiers are nothing but a modified version of bilinear attention. So ideally, if you just look into the equation here, for bilinear attention, we compute the outer dot product of the function and sum it up with the linear function. So U and W are the tensors and metrics, which are the learnable parameters here. And we pass it through a softmax layer to get us the final probability. And likewise, for the back propagation, the model is being updated for end-to-end purpose, right? So that's why we train a model, and it helps to achieve performance where it handles the scenarios which were being faced as a challenges during our traditional techniques. So considering the next scenario, let's talk about clinical predictions, right? So clinical prediction is a task of predicting the likelihood of a disease within a window, a frame of time, by modeling the sequence of clinical events. Okay, so just observe this original note here. So if you observe this note, what we have here is sequence of medical conditions of a patient, which is separated by colon, which is nothing but at a patient encounter level, right? So a patient went to a doctor, gave his say a patient is suffering from heart, is doing heart diagnosis, heart failure diagnosis, and he goes for this chronic disease to a doctor, and every time doctors gives him a medication, he does the diagnosis, give him some procedure and other following information, and we have all these informations being available with us in our EHRs and other source of electronic medium. And then what we do, we use these historical data to predict if the person will face a diagnosis positive or negative for a specific disease in the coming days or a period, right? So to explain it in simple terms, you can understand, I have put in the prediction task here. So what we do, so we consider, we observe all the clinical notes which has the diagnosis, the condition and other information available of a patient for a historical window of time, right? So say for the past 12 months, past 14 months, you will observe for a patient all his encounters, and you will then using those as your input, you will predict for the upcoming possible encounters whether he will be diagnosed positive or not. Okay, so the key thing you are observing here is that while considering the history window and while making the prediction window, we leave a gap in between them. And why we do so? Because it's important for us to prevent the model from learning the information which was generated just before the diagnosis time. right? Because the ultimate idea of clinical prediction is to predict a disease which is to be diagnosed before it is happening, right? So we create a gap of say 3 months. Okay, so we consider 12 months historical data, create a gap of 3 months, and then we do a prediction for ahead of 6 months, right? At the possible encounters, when a person is going to and expected to be diagnosed, and when, right? So that is where we capture these gap to encode the same information in our training set as well. And to build this model, what we do, we consider all the representation of the patient. So features will be your patient information at each encounter, right? So T1 is patient visiting the doctor at first, then the subsequent, then the third time, fourth time, right? So it represents an encounter, and within the encounter, you will have his diagnosis history, his medication history, and the procedure being guided. So we consider these information and represent them at a patient level by encoding them through vectors, and we pass this embedding to our CNN layer. So ideally, there has been various research being taken how to encode this information well. So ideally, there has been a stacked approach being proposed, which has been proven to work well. So what we do, we feed this patient's representation to our CNN model, which has a large kernel, and we extract the embeddings from them. And then we feed these embeddings to a GRU layer. So GRU layer, as we understand, what it does is here it's that it learns the temporal relationship which has between the disaggregated features. For example, at T1, a medication was ordered, and at T2, the procedure was being done, right? So that temporal relationships are being modeled by GRU, and then the output what we get and the final output, we add our initial patient information like gender, age, and other so categorical information to the dense layer, and then we apply our forward pass with an attention layer to say that okay, for the next possible 6 encounters, when he is going to be diagnosed, if he is going to be diagnosed positive, right? So we create an end-to-end architecture. So concluding and considering what are the challenges we have in implementing this deep model. So one thing is that ideally these data sets, depending on the problem it has, right? So ideally you will see that the patient data set is not easy to be shared because of various compliance and privacy. So the model, these deep models generally do overfit very easily on the small set. Also, you will see that there is a challenge of generalization across a population. Okay, what does it mean is that suppose you are building a clinical prediction problem. Say for the patient, you took a population of a patient which were say elderly patients. Okay, and you predicted a model and you got a good performance. And same if you will try to leverage and do inference on a different population, say a pediatric population, for example, right? So you will see your model getting totally tossed up. So there is a lots of challenges in generalizing across the population. And of course, as we understand that these healthcare concepts are very dependent of the therapy, right? So an oncology therapy will have a different totally corpus or a say different therapy, right? So they vary through therapies. So that's why there are lots of semantics and syntactic variations within the corpus of the therapy, which is that's where you'll see the lots of features are not getting learned well. And as much as it is important to train the model well, it is also important to make it interpretable, right? Because at the end you will see that these models will play a critical role in terms of assessing the doctors. So what it has to be that the users will have an expectation that they want to know that what features or what factors the model has considered to make this decision, right? And overall you will see that as these models have a large number of parameters and they are complex and big, right? So it requires the training cost which gets multiplied depending on your data size as well, right? So considering this challenge, it's very important to build a hybrid approach. So the right approach will be a combination where you will observe your data patterns, your data type, and you will also look into the model complexity with respect to the problem you are solving, right? So you will look into the what problem you are solving and what data and what algorithm is working for you, and accordingly you will generalize for the best fit. Okay. So with this, I conclude for today. So the overall idea was to give you a brief understanding on the applications available in healthcare domain and discuss on the few key applications and how do we solve them with these NLP concepts. So let me know if you have any questions. I'll be happy to discuss.
No, yes, sir. There are a few questions from the audience side. I'll be popping them on the screen right now.
Okay.
Yes, sir. This is the first question from a student named Lazy.
Okay. Is there any reason not to use SOTA technique for sentiment analysis? The number of parameters are concerned. See, so of course, right? So what do you mean by SOTA technique is very subjective. So the SOTA technique is, of course, when looking into the research perspective, it looks into the problem statement. When you talk about the application perspective, it depends very much on the data you have, right? So a SOTA which may work on the financial data will not may work on the healthcare data. So it's very much dependent. So that's where it's always ideal we look into the hybrid approach rather than straight going to the complex models and leveraging them.
Yes, sir. Thank you, sir. Now I'll be popping the next question.
Okay. What is the application of adverse event detection use case that you explained? Is that the patient side or for the providers? So of course it's for the providers. So ideally these adverse event detections are typically applications of pharmacovigilance. So say you are a drug company and pharmacovigilance is an activity of monitoring what is the drug usage and its efficacy post the marketing once the market drug is being launched into the market. So you as a company would like to monitor how the patients is being observed, what all side effects they have been placed, and accordingly revive your patients population.
Okay, sir. I'll give the next question.
Okay. What is the benefit of using CNN instead of any sequence model like LSTM for a text data? Right. So of course, that's a very interesting question. So what happens here is that in LSTM we capture the sequences, right? But you will observe that the CNN captures the semantics very well. So ideally, if you see that an ideal model is that you consider the feature representation of your vectors, feed it to the CNN where you learn the semantics encoded into a lower dimension, and then pass it through LSTM where you learn the sequence and then do prediction. Right. So it's a combination of both.
Yes, sir. Thank you, sir. The audience were too interactive. There are pretty much more questions, but due to the time restrictions, I would ask the audience to get offline and ask sir
Sure, sure,
certain
sure.
questions
So
offline.
I'm available on all social media handles on Twitter and LinkedIn. So you can just search my name Swayam, and I hope you can connect with me. Sure.
Yes, sir. All the links are in the description. Thanks a lot, sir, for
Thanks. You.
taking
I
the
hope you
time.
all guys find best. Yeah.
Yes, sir.
Thanks.
Thank you. Now, co-anchor Rituraj will be starting the introduction for a third speaker. Over to Rituraj.
Thank you, Prahasit. Good evening, all. Recommendation system is omnipresent, be it YouTube, Facebook, LinkedIn, or Amazon. Most of the surveys predict recommendation system to be a 12 billion US dollar market in another just 3 to 4 years. To give you a quick overview of recommender system, we have Mr. Saptarishi Goswami, who is assistant professor of computer science at Bangabashi Morning College, affiliated to University of Calcutta. Welcome, sir. Yes, sir. Yes, sir.
So as explained, recommender system is quite an important subject. Okay, and
S-
one of the
uh, Hello, sir. Sorry to interrupt, sir. Can you adjust the volume? So the mic volume is a little low.
is it better now?
No, sir. It's a little bit more.
All right. Okay. Okay. Let me try. Let me try.
Yes.
Yeah. Is it better now?
Yes, sir.
Okay. Yeah. Sorry about that. Okay. My objective would be to give you a
overview or introduction to recommender system, both from an academic point of view. So I'll discuss about different components, different types, different research issues, and then I will also try to give you some tips on how to get started on your research or your some application works on recommendation. Okay. So, this is a very brief background of mine. So, I am also a member of this, life member of this Mass Research Club. You already know that there are more than 500 members across India. And there is also this initiative, Mass Academy. Okay, so where there are very application-oriented courses, as explained by Joy, and associated with Society for Data Science. So the websites links are there. I'm not going into discussing that. And then you may be knowing about Open Data Science Conference. So we have a community in Kolkata. So I'm working as a meetup ambassador of ODSC Kolkata. And then, as part of my research, like our Calcutta University Data Science Club is actually part of laboratory of interdisciplinary statistical analysis, okay, which is called as VISA. So it is headed by University of Colorado Boulder, and my research interests are feature engineering, natural language processing, and time series forecasting. So feature engineering has been my core topic of my PhD on the topic that I have done my PhD, and there are some research that we are doing on natural language processing, okay, and there are some amount of time series forecasting that we are doing for renewable energy, especially on the solar energy domain. So we are soon to start on the wind energy part. Okay, this is my Google Scholar link. So you can look at around 50 publications that I have published so far. Okay, and if you have interest on any one of them, we will definitely be very happy to answer those. Okay, and this one is our YouTube channel from Calcutta University Data Science Lab, where there are plenty of videos available on classification, clustering, neural networks. Okay, so you may even take a look at that. All right. Okay. So now let's get started on the topic. So we are going to discuss about objective and goals of a recommendation system, its different types, some of the issues it has got, and then we will also look at approaches of recommendation, which are like neighborhood based, model based, matrix factorization based, deep learning based, and then we'll also look at some of the evaluation methods. Okay, so that's kind of the overall plan that we have. Okay. So let's now go ahead and look at the basics. So as was being explained to you, that recommendation is all around us. So be it music recommendation, be it app recommendation, be it video recommendation, right? Be it recommendation about what flight you are going to take. So this screen must be very familiar to you. This is from LinkedIn, where some connections are being recommended, okay? And these are YouTube video recommendation, and recommendation engine market size, as again was explained, is slated to grow at a 32% year on year. Okay, so that is why it is very important that you start appreciating the different nuances that are there in recommendation engine. Okay, and finally, I have also kept this book's name, okay, which was recommended to me by Amazon. So product recommendation, it was there for long time. Right? Okay. And actually 40% of the apps that are installed on Google Play actually comes from recommendation. Okay? And 60% of our watch time on YouTube also comes from recommendation. Okay? So just to tell you how important and what is the market size of recommendations. Okay? And when we talk about recommendation, we cannot overlook the Netflix context. So this was launched in 2006. Okay, and it was there for around 5 years. Okay, and actually this took the community by a storm. Okay, so there are a lot of developments which happened because of this Netflix challenge. So at 2006, the prize money was $1 billion, right? So you can assume like that was 15 years back, right? So it actually it actually propelled the community a lot. So you should definitely look at this resources. Okay, so the data set is also available publicly, so you can run your own code and see how you are doing
Uh,
with good solutions. Hello.
Sorry to interrupt you, Saptarshi. Your screen is also very hazy, and the audio is also poor. Just can you resolve, because we can't see anything. It's all coming hazy. Joy here.
Yeah, yeah, okay. My internet connection looks okay, so I'm not sure. I can change to another, but I don't think that will better. So how about others? I mean, Sam and all. Hello.
The screen is hazy a little bit, and the
This one,
volume.
this particular slide, or all of the slides?
I guess all of these slides.
So this
Uh,
particular slide or all that?
so all of these slides, even this one.
These slides are unclear, sir.
Okay. So maybe this has got a little bit of text. Okay. So this, as I was explaining, that this came around 2006 and gave a lot of things to the community. Okay. All right. So now let's look at some of the components that are there in the recommender system. So the basic things are your user, your products, and your preference or rating, right? So these are the three things which are essential, and this preference or rating can be implicit as well as explicit. Explicit. So when we say explicit, so you give ratings like this, right? So you give star ratings like this, and when it is implicit, okay, so it can be that the user has watched the movie but he has not rated it, right? So he has visited the website but has not made a purchase, right? So these kind of implicit feedbacks are also there, and how the data is represented generally. So it is represented in terms of a matrix, right? Where the rows are your users. So these are your users, and this example is for a movie, right? So these are the movies that you have got, okay, and these are the corresponding ratings. So this user has rated these two movies, right? And this particular matrix has got a name attached to it, which is called as preference matrix or utility matrix. Okay, all right. So, what are some of the formal objectives of recommendation system? So, as we discussed, that we are given a M into N matrix, where M are the number of users and N is the number of items. And you can understand that it is an incomplete matrix, right? As not all items are rated by all users. So the rated items are now used to predict the items that are not rated, right? So very similar to our machine learning type of formulation of the problem. And another problem, which is kind of little specific, which is top item. So instead of predicting all the items, uh, we try to predict top k items to be recommended for a user. So if k is the value, k has the value 3, and we are predicting movies, so we are just predicting top 3 movies for a particular user. Okay, and similarly, the problem can be formulated back. So if there is a new movie, you can also try to find out who are going to be the top k users. Okay, so this is the formal objective of a recommendation system. Now let's look at what are the goals and types of a recommendation. So of course, one of the goal is that the recommendation should be relevant, right? So if the recommendation is not relevant, the user will not be interested in it. Second is that it should be novel, right? So there should be some amount of exploration that happens. So this is one of the areas where it starts getting different from your traditional machine learning. And then this should also have some amount of serendipity. So one of the examples that you can see a lot is that a person, who is very fond of, Indian foods, okay, if there is a new Pakistani restaurant that has come up, maybe that restaurant will be recommended to you, right? So it is not very obvious. There is some amount of novelty, but maybe there is not much of surprise element, right? So surprise element will be maybe you are being recommended something from an Ethiopian restaurant, right? So what the user has not actually experimented, and there may be a chance that he will like it, right? So if you think about the relation between novel and serendipity, so all serendipity items are actually novel, but the vice versa is not true. And similarly, you should also have enough amount of diversity, all right? Because if a person likes some, so if he likes maybe burgers, you just recommending all burger outlets, so that is not a very good thing for the recommendation system. And what are the different types? So types are content-based, collaborative, knowledge-based, and hybrid. Okay. Now, mostly, we talk about collaborative recommendation system. So that is what we will go into little bit depth. However, we will also discuss about the different types or what each of these different type of recommender systems are. Okay. So the first is your content-based filtering. If you look at this diagram, you see that there may be data available to you that a user has watched some movies, okay,
Excuse me,
and he
sir.
has liked that movie. Yes.
Sir, sorry, sir. Sir, can you share the slides with us? We will share it on the screen. There's some screen issue still. It's hazy.
I'll do that.
You can put it in the private chat. So
Oh, can I attach it here? Can I attach in the private chat?
Yes, sir. So you can send the link.
Oh, it's not uploaded anywhere.
sir, do you have done it in the Google Slides or the PPT Microsoft thing?
No, it's this. So let me try again. So it has not happened earlier. Let me try sharing again. Okay. So maybe can you
So you can attach,
yeah,
sir, in WhatsApp group or anything that is convenient.
yeah. So just see if it is better.
Yes, sir. It's better than before.
So give it
Can you
some
go for
time.
the full screen, sir?
Yes,
Yeah, sir. Now it's better.
Now it's good.
yes, yeah. Okay, okay. Sorry about that. Huh? Yeah. So what we are discussing was this content-based filtering. So what you have is you have users. You know that user has liked some movies, right? So what you do is you find out movies which are similar to the movies which are watched by the user or rated well by the user, right? So what happens is so the some of the salient points about content-based recommendation is that it considers the static characteristics of the movie, the genre, the description, director, actor, to find similar kind of movies, right? And a user-specific model is created. Okay, so you already have a training set where you have the items which are rated by the users. Okay, and the rating is the target variable in terms of your traditional machine learning terms, and these descriptive features work as the input variable. So for the test set for the movies that he has not watched yet, you try to use them as input and try to find what would have been the rating of the user. If the rating would have been good, to recommend those to the user. Okay, so that's how it works. What are the advantages? So advantages that can work when other users rating is not available. Okay, so it does just needs the description of the movie or the book and your own rating or the user's own rating. And new items do not suffer from cold start problem. it says suffer, so there is this mistake. Okay, and the disadvantage is that it gives obvious recommendation. So I was talking about novelty and serendipity, right? So if you are just going to look at the description of the movie and find similar movies, of course it is not going to give you the novelty. Okay. So the next one is called as collaborative filtering method, which has two types. The first type is called user, and the second type is called item. So for both of them, the starting point is an user. So what we do over here in user, so we have a user. What we do is we try to find out users who are similar to him, and then I find out that what are the movies these guys have watched. Okay, taking an example of movie recommendation, what are the movies these guys have watched, but this guy has not watched. And if there are some unwatched movies like that, I recommend those movies back to this user. Okay, and whereas item, what happens? So this user has already looked at some items. Okay, and you look at which are the items similar to those items, right? So these items which are similar, okay, and then you recommend back these items to this user, right? So you might be a little confused here, and it might look very similar to content based and user based collaborative filtering. Okay, so now in content based, we are finding similar items based on the description of the item. But here we find similarity of the items based on how different users have rated them. Okay? So that's the subtle difference. So many of the literature or many of the blogs you will see that they don't report this difference very correctly. So next we have something called as knowledge-based recommendation. So knowledge-based recommendation happens when those items are not very frequent items. Okay, so maybe real estate. So you don't buy a house every day, right? So for that you don't have enough ratings available, enough similar users available. So what you do is you try to build knowledge by asking users or asking some queries from the user, and then you use those information to find out good properties according to the knowledge that is already given by the user. Okay, so this is a more difficult domain to work on. Okay, and then you have something called as hybrid recommendation. So as the name suggests, so here what you do is you apply multiple strategies. So you can apply content based, you can apply collaborative, then you can apply some kind of intersection and find that out. You can use them in pipeline, you can use some kind of easy, less expensive filtering techniques to actually prune down your problem space, and then you can use some computationally expensive methods. Okay, all right. Now let's discuss about some of the problems in recommender system. So I'm going to discuss only two or three of them. So one of the problems is called as cold start. So as we were talking about collaborative filtering, which depends on that the items rating already available or the users rating on items already available in the system. But it may happen that the user is a new user, right? Or it may happen that the item is a new item. So how do you actually recommend that? So this particular problem, is called as a cold start problem. And if you think about it a little bit, we'll realize that the collaborative filtering are more prone to this cold start problem than content based, because content based just needs the description of the item and the user's own rating, right? So it doesn't need other users' rating. Another problem is called as attacks in recommender system. So basically, what happens is that this is as I said, that this has a quite a big market size, right? So users or companies will try to put their products with high ratings, okay, high rating, good reviews. And for that, what can be done is that a company can insert malicious users or fake profiles, right? So this can either increase the rating of your own product, okay, or can reduce the product of your competitors, right? So one is called as a push attack, okay, and another is called as a nuke attack, all right. And when you create such kind of fake profile, this is called as shilling attack. So you want to design the recommender system which is attack resistant, right? And another problem that happens or the recommendation system suffers is called as a long tail problem. So what do you mean by long tail problem? So basically, only some of the popular items get a lot of rating, right? Not all, and there can be several items, okay, several items which are not rated at all, okay. So this problem is called as a long tail problem. Now let's quickly look at some of the recommendation system approaches. That how do you design such system? So one such thing is called as neighborhood-based collaborative filtering approach. So this is a typical metrics that will be available to you, and what you need to do is you need to actually find out, okay, these two ratings. So this I am taking as an example, right? This question mark is what I want to find out. So what I'm going to do, I'm going to find out that which users are similar to this user 3. How do I do that? I can use a simple correlation formula to find the similarity, right? So what I can do is I can find its mean rating and deviation, and then I can find the covariance. I can divide it by the corresponding standard deviation and get the correlation between the users. And if I calculate this, you see that this particular user has correlation of 0.894. The next user has 0.939. 1.0 you should ignore because correlation with yourself will always be 1. Okay. And for the fourth user it is -1, and the fifth user it is -0.817. Okay. And if you remember about correlation coefficient, the value comes between -1 to +1, and more the value, right? More the value, more similar the user is. So if I am looking at top 2 users, what I am going to look at is I am going to look at these first 2 users, right? These 2 users are more similar to user 3. And now if I want to find out the rating of this particular product, what I'm going to do is I'm going to use these 2 as an input. Okay. Similarly, I can use these 2 as an input. Okay. So here, instead of using any model-based technique, we just average it out, and it will be a weighted average. Okay. So I can multiply 7 with this weight, 6 with this weight, and I can say that this person may have rated this around 6.5, and the sixth item, both of them has actually rated 4, so of course the average will also be 4, right? So this is one of the ways, a very simple way by which I wanted to illustrate this. But there is a problem, you might have seen that some people gives a very high rating, so their range may be 7 to 10, and some people may have very conservative range, maybe 3 to 7. So some kind of adjustment can be done to accommodate that. So I'm not going into that detail. All right. Now let's look at some more about this neighborhood-based method. So the rated items actually constitute of your training set, and the unrated item consists of your testing set. Okay. And neighborhood-based methods are very similar to your KNN classifier. Okay. Popular items actually inflate the rating. So some users have turned only has rated the popular items. So 2 users are very similar because of that. Okay. So it is kind of an imposed similarity. So you can handle kind of TF-IDF that you do for text. Okay. And then item-based recommendations are more accurate because users' own choice are being used for recommending. User-based recommendations. So when I say item-based recommendation, what I am saying is item-based collaborative filtering. Okay. So they are more accurate. User-based recommendations are more diverse. So this will give you more novelty or more serendipity. And when malicious or fake profiles are created, item-based recommendations are more robust. You can understand that, right? And both actually suffers heavily from high time and space complexity. Okay. So now let's look at from neighborhood-based approach. Let's look at model-based approach. And when you are looking at a model-based approach and your traditional classification, if you arrange in terms of rows and columns, okay. So these shaded areas are actually your output variables. Okay. So you have your training set and testing set in a classification problem. However, when you do for a recommendation system, this is not a fixed column. Not only that, you cannot clearly differentiate training set and testing set, right? So if you want to use your traditional machine learning model, you can use it. So how you can use it? So build separate models with each item's rating as a target. Okay, so each column you can make it as an output variable and do the training. Okay, and also there are a lot of missing values. So one of the challenges of recommender systems, of course, that there is lot of sparsity, lot of missing values. So you can apply some dimensionality reduction technique, which is also often called as an embedding. Okay? So this is one of the techniques of using embedding. Okay, so you use matrix factorization. So idea is very simple, right? So the idea is that you have a matrix like this, and you want to subdivide, or you want to find two small matrices, okay, which you multiply, you will get back this matrix. Okay, and you assume that one of them corresponds to the item, and another of them corresponds to the user. So you call them as user embedding matrix and item embedding matrix. And what you want, what is the objective, what should be the similarity between these two matrices? So they should be approximately equal, okay, or they should be as close as possible. All right. So what we are going to look at is now what is the objective function. Okay, so this is your original matrix, right? This is your original matrix value. Okay, aij represents a cell value, and what you are doing is you are multiplying a particular user embedding and that particular items embedding, okay, to get the rating that you will get from this reduced format, right? And this should be minimum, okay, for all item user embedding. Okay, and this is a specific format. You can generalize it more. You can say that I will differentiate between the items that are rated and the items that are not rated. Okay, so you use a weight parameter over here, okay, for the not rated item. Okay, as it is 0, right? So you have not put it in that format, right? So here aij is actually 0, right? So you try to minimize that, and any objective function you can solve by your stochastic gradient method. So there is also a specific weighted average least square method which can be applied for recommender system. It has more loss function than the one we have discussed. However, it converges slow, okay, and not good for other items. All right. Hello. Uh, Hello.
Hello. Yes, sir.
So, yeah. Okay. So, you can also formulate it in your neural network terminology. So, what you are going to do is you are going to use your feature about movie. Then, then you want to recommend different items, right? So, output is your different items, right? A probability vector with the size of the movies, and the input is generally user query. The user query can come from the user itself, or you can create the query of the user's past experience. So that can give you either a sparse feature or a dense feature. Okay, and you can also create two neural networks for embedding. So one neural network can map the query features to query embedding. Okay, and another neural network can map the features to item embedding. Okay, all right. Now let's come to the problem of evaluation. So how we evaluate the recommendation system? Okay, so you can think it to be an extension of classification and regression model. So similar evaluation measure can be used, and it can be both online and offline. So here there is a little difference. So of the machine learning models or the deep learning models can be quite offline, right? But here, because you have a testing set available, you know what's going on. But for recommendation system, you actually want to know when you are recommending something, whether the user is taking that or not, right? So that is called as an online evaluation, okay? And you can apply A/B testing for that. So A/B testing says that you evaluate or you distribute your users in two groups, A and B, and you expose them to two algorithms algorithm, and you see which performs better. Okay, and having a large scale system for online evaluation has its own challenges, right? So many of the times you have to go back and use your historic data set, okay? And traditional measures like accuracy will not be sufficient. We need measures to calculate novelty, diversity, etc. So, this is your standard measure, accuracy, right? Uh, where actually you can use your RNAC, you can find what was the actual rating and what is the rating your system has recommended. You can also look at something called as catalog coverage. So it tells that out of the items that are there, how many of them are you are recommending. So it may be that you are recommending only the popular items. So that is not an objective, right? Another is called as novelty. So this is calculated using differential accuracy. So basically, what you want to do is you want to predict not only what the user is going to observe now currently, but how his taste is going to be evolved in the future. Okay, and then you try to find also the diversity. How do you find diversity? So you look at the recommendation to find out the similarity between the items, right, in the recommendation, and you take an average. And how about calculating the serendipity that we are talking about? So we take a primitive recommender, right, a content-based recommender, and we look at its recommendation. Okay, and then we'll see the proposed systems recommendation, and we'll see that how many of these are actually recommended by the system that we have proposed. So if the intersection is less, that means there is less serendipity. If the intersection is less, that means that you have more serendipity and vice versa. Okay, and these are some of the resources that I want to give you. So basically, what I want to tell you is that you cannot replace books, right? So there are a phenomenal series of books by Professor Charu Agarwal. This is not only on recommender system; it is on neural network, it is on outliers, it is on text and NLP, all published from Springer. So books, of course, you can look at some of the Kaggle competition. So this is one of the Kaggle competition. So what I'm trying to say is that not only theoretical knowledge you'll have to apply, and of course you can look at some of the research papers, right? So this is one of the papers which has got good citation from expert systems with applications from the Elsevier publishing group, okay, which particularly talked about cold start problems. And of course, then you have institutions like Master Academy where you can solidify, interact with the community and apply through different practical case studies. Okay, so I think that brings us to the closer of the presentation, and I'm really sorry that there are a lot of interactions today. Okay, fast time for me as well. So really sorry for that.
No problem, sir. Thank you so much, sir, for such an informative and such simple ways of explaining things. Anybody who wants to get in touch with sir can contact him on his social media handles. Thank you so much, sir, once again for sparing some time and gracing us with your presence. Over to you, sir. Thank you, sir. Thank you, sir.
Thank you, sir. So the next speaker for the session is Deepanjan Sarkar, who is a data science lead at Applied Materials and who is also a Google developer expert in machine learning. For the topic generative deep transfer learning for computer vision.
Can you hear me?
Yes, sir, we can hear you.
Okay, great. Let's get started. I'll share my screen. I hope the presentation is visible.
No, sir, it's not yet visible.
Okay, that's strange. Let's see. Can you allow the content? I'm just sharing.
Yeah, sir, I guess yes, sir. We can see the screen.
Okay, good. Yeah, so everyone, thanks for joining in today on the weekend. I'll be covering a couple of aspects of generative deep transfer learning for computer vision. It's a heavy topic, but just to motivate the fact that the idea is nowadays we are moving into the advent of deep learning, where we are looking at more and more unstructured data like images, text, and so on. And we are also trying to potentially look at ways in which we can leverage more complex models to solve increasingly complex use cases like style transfer, image generation, image translation, audio translation, and so on. So today's domain is computer vision. And we'll be looking at a separate aspect of deep transfer learning. Typically, we have seen supervised aspects where we usually have some kind of label data and we are doing a regression or classification. But today we are completely generating images from scratch. So it'll be interesting. So there are three aspects here to understand a brief about transfer learning for the people who are new to this domain. And then we'll dive into two use cases. And this is again hands-on. So we'll look at how do you actually do these things through code. The first case study is image super resolution. And the second one is neural style transfer. So let's get right into it. Can we also enable the video as I'm presenting so people can also see me and understand? Hopefully that will be a much better way of interacting. Now, let's talk about myself briefly. I guess a lot of you might already know me, so I won't take too much time here. But basically, as introduced, I'm a data science lead at Applied Materials. I'm also a Google developer expert in machine learning. And also, I'm a life member at Must Research and also a mentor at Springboard. And besides this, I also publish my work frequently from time to time online on GitHub, Medium, and even on LinkedIn. So first of all, thanks to TensorFlow user group. And like I said, I'm also a life member at Must, and do join us if you're interested to do some serious research in the area of artificial intelligence and data science. And also for people, as Joy introduced, for people who want to learn like a more interactive approach towards data science, definitely check out Must Research Academy, where you will be kind of introduced to various types of programs which give you both a hands-on perspective as well as a research element to it, where you can even publish potential research papers based on the work you do. So diving into the content, transfer learning brief, let's understand about how transfer learning is different. So the idea is, as you already know, traditional machine learning or deep learning is where you have some kind of models being built based on a specific task you're solving. Now, if you have to solve a new task, you build again a model from scratch in isolation. So here, learning is not shared, knowledge is not retained. Everything happens in isolation based on the task you're trying to solve. As you can see here. And for transfer learning, the idea is if I already have built a model or built some models on a large data set, can I leverage that knowledge from the pre-trained model into a new problem onto a new data set based on a task I have to solve? So this is where the retained knowledge is used. And typically this knowledge is used in the form of feature representations from the model in terms of weights and so on. Now, going into the next slide, transfer learning about the pre-trained model advantage. So what's the advantage of pre-trained models? Training deep learning models from scratch can take a lot of time. And also for areas of low data problem where you don't have sufficient data, you can leverage these pre-trained models instead of training a model from scratch, and you may get better performance. And they have been specialized to perform specific tasks. I think in some of the previous sessions, as you got a feel about like object recognition, segmentation, and so on, there are different tasks. So there are a lot of models which have already been pre-trained and they perform really well. So what you can do is you can just take that, fine-tune it on your annotated data, and you can get going. So that's the advantage of leveraging pre-trained models rather than training from scratch. Let's dive into the first use case. So this is image super resolution. So what is image super resolution? As you can see in this example here, the idea is to generate a visually pleasing high resolution image from a degraded low resolution image. So as you know, typically images come in different sizes, dimensions, and resolutions. And the idea is if an image is having a low resolution and I want to resize it and let's say bring to a higher dimension and a higher resolution image, how can I retain the visual quality of the image? And it's definitely a very interesting problem and also has some practical significance, not that you just do this for fun or something like that. But as you can see, like security and surveillance imaging, medical imaging, image generation, there are various types of domains where image super resolution can really help, where you may start off with low resolution images, but if you really magnify it, you can see various things which can help you in your tasks. So that is the whole premise of this use case. How can I basically increase the resolution of a given low resolution image to high resolution? And now let's talk about the library which I have used here. So typically there is this open source framework called Image Super Resolution. This has been built by Idealo Tech. And my friend, good friend, Fran, many of you may know him on LinkedIn. He, along with Francisco, has kind of built this framework over quite a fair bit of time. So we will be leveraging this framework for our hands-on tutorials, and it's available on GitHub, by the way. I'll share the link again at the end of the session. So I would encourage for people who really want to like train their own super resolution models, do check this out. It can really help you plug and play with different types of super resolution models based on the latest state-of-the-art research. So what are the typical model architectures? So let's say you want to dive into the world of image super resolution. Typically, you will need to start with some research. So what are the existing model architectures out there, which researchers have painstakingly built over the last several years? So these are the key models based on some of the research I've done recently to see what other people have actually built, because that is the best way in which you can start something rather than reinventing the wheel. And obviously, people like me who is working day in and day out, they are not like sitting and doing hardcore research. So hats off to all the super serious researchers out there who have built these models. So these are the typical models. As you can see, the first one is called the residual dense network, and it is based off this architecture. We'll see this in more detail in the forthcoming slides. It's based on this concept of a residual dense block. So that is what we will see, where the residual dense network uses these RDBs, and one step above or an improvement from the residual dense network is the RRDN, also known as the residual in residual dense network. So it's just like the inception, where you're having an RDN and now you're plugging in multiple RDNs with residual connections. And the last one is where you leverage a generator and a discriminator and use the GAN approach to train an RRDN with the discriminator and try to build a better model than its individual components. So that's the last kind of an architecture which you can look at. There are relevant research papers for this, and I'll share that towards the end of my presentation, so people interested can dive into it. So what's the ISR training workflow, image super resolution training workflow? The first step is obviously to build any model, you need some kind of training data. So there is a lot of label data available. The diverse 2K resolution data set, also known as the div 2K data set, it's an open source data set, and it has been used in a lot of competitions also. So you can get this data for free, and it's open source. So what it gives you is basically the same image in a lower resolution and the same image in a higher resolution. So you get the point. It's basically a paired component of a LR image and a HR image. And the idea is, based on so many of these images, can you build a model which can learn the right representations so that in the future, if you give a new LR image, it can translate it into a higher resolution image. So once we get this data, the idea is you need to create the model architecture. So we will leverage the RRDN model. And then what we'll do is we'll also leverage a GAN-based training approach where we will use a discriminator network, which will help us in basically saying whether the generated image is like a fake image or not a fake image. So the idea is to get closer and closer to the high resolution image. So that is what we'll be using. And the other part is, by default, these models use the peak signal to noise ratio. People from image processing, this term might be familiar to you. Basically, it's a pixel-wise mean square error. So this is the loss used. But what we will be using here is known as the perceptual loss function. So the idea here is to kind of improve the performance, not by just taking a pixel to pixel-wise mean square error, but a more improved version of this loss. And how this will be used is we will not just train on the loss based on the actual generated image and the high resolution image difference, but also we will be leveraging the VGG19. As you know, it's a pre-trained model from the visual geometry group at Oxford. So we will actually be using this model to extract some feature representations from, again, the LR and the HR images. And then we will try to compute the perceptual loss of those deep feature sets also. So that is something you should keep in mind here, that we are not just training on just the PSNR loss, like a pixel-wise loss, but also based on this perceptual loss, which is something which has proven to give like visually pleasing results, and definitely much better than the base PSNR based loss. So what is the residual dense network? The core components of a residual dense network, again, this is taken directly from the paper, which I'll be referring at the end. So the core components is one, initially it starts with some shallow feature extraction layers, some shallow convolution layers, as you can see here. This is known as the shallow feature extraction net. And then comes the core component or the core innovation, which was done by the authors of this paper, called the RDBs, right? The residual dense blocks. And if you expand the residual dense blocks, you can see here that it is a bunch of conv layers and activations. And you can see there are skip connections from each to the next one. So basically, it's like a dense connection, as you know, a fully connected dense neural network where every node connects to the other node. So that is exactly what is being done here, a combination of these conv blocks along with a fully connected dense connections. And also there is a residual learning, as you can see, a skip connection is here. So a combination of a residual connection along with dense connections and conv blocks gives you this RDB, the residual dense blocks. So as you can see, it allows these direct connections from the preceding RDB conv blocks to the next ones, as you can see here. And we also have a residual connection. So basically, having all of this enables it to learn what is known as a contiguous memory mechanism. And local feature fusion is also a concept which is used to adaptively learn more effective features from both the preceding and the current features. So as you can see, that is the reason for using these dense connections. And then once we have this local feature fusion, what also happens is called the DFF, the dense feature fusion, also known as feature fusion on a global level. So this is where it jointly and adaptively learns global hierarchical features, which ultimately helps in preserving the specific components of the image to give visually pleasing results. And the last part is obviously the upsampling, because we have a, let's say, image of X dimension, and we will upscale it to 4X. So that is where this effective subpixel CNN is architecture used to upscale the coarse resolution features into the finer resolution ones to give that super resolution or the high resolution image. So this is the concept of the residual dense network. And these are the high-level parameters which are being used in our models, as you will see later on when you want to configure them. Like D tells you how many residual blocks do I want. C is the number of convolution layers which I might want inside an RDB. G is typically the number of feature maps which would be there inside each convolution layer. As you know, sometimes we will say like, a convolution map of size 3 cross 3 comma 64. So 64 is like the number of feature maps. So that's the number of feature maps. And also G0 is the number of feature maps for convolutions outside the RDBs typically, and for the RDB output. So these are some of the parameters which you will typically use to construct these residual dense networks before you go for your training. And the next one is from a paper called ESR GAN, Enhanced Super Resolution GAN. And that is where it introduces an even better architecture called the RRDN, Residual Dense Network. And the whole premise of this is it was built based on a model called the Super Resolution ResNet model, which is what you're seeing here, which includes some convolution blocks, the same upsampling block, and something called as the basic blocks. So what happens is these basic blocks have been replaced by this new concept called this RRDB, the residual dense block. So what are these basic blocks? So basically what it gives us is it combines multi-level residual networks and dense connections. So as you can see here, earlier we had just like a one level of residual connection here, and then these were being used here. Now, as you can see here, there are multi-level residual networks being used along with a dense connection. So multi-level residual networks, multiple skip connections are being used everywhere. And obviously, multiple dense connections are also being used. And one more advantage or change which has happened is it has removed the batch normalization layers, which you remember were there previously. It's not represented here in this picture, but in the original paper, if you go back and see, typically for a residual block, as you can see here, the RB, there is a BN layer typically. So there will be BN layers between every convolution blocks. So what has happened is this has been now removed with regard to the RRDB, the residual dense block. So the idea is combine multiple residual dense blocks by removing the batch normalization layers and introduce skip connections in between them. And as you can see, because of removing the batch normalization layers, the authors of this paper has observed that it has proven to increase performance, remove unpleasant artifacts, blocky artifacts from the image, and also improve the generalization ability. So that is something which has helped in this being an even better model. And also they use what is called as a relativistic discriminator, where you try to predict the probability that a real image is relatively more realistic than a fake one, where it computes the expectation of all the fake images in your batch and it subtracts it from the representation which comes out from the real image in the discriminator, versus where a normal standard discriminator just says whether the probability of a real image is real or not. So that is something also which they have used, which is different from a standard discriminator approach. And these are the standard parameters for the RRTN. In the interest of time, I will cover this quickly, where T is the number of RRDBs, the residual dense blocks. D is the number of RRDBs, D is the number of RDBs which are being used inside every RRDB component. So you can have multiple RRDB components, and inside every RRDB block, you will have multiple RDBs because you need the skip connections also. So D is the number of residual dense blocks inside each RRDB block. C is basically the number of convolution layers inside an RDB, just like the previous RDN model. G is the number of feature maps for the conv layers, and G0, number of feature maps for conv layers outside these residual dense blocks, just like before. So these are some of the parameters which we often use to build our models. A brief on the loss optimization, which happens during training before we go into the next step. So typically, super resolution is the generated image from the low resolution image, as you can see, once it goes through the RDN or the RRDN model. And what we do is we compute the MSC based on a pixel-wise loss computation between the generated image and the high resolution target image. But what we are also doing in this case is we are extracting deep feature representations from passing these images. And by these images, I mean the generated super resolution image we are passing through the VGG, and the high resolution target image also we are passing through the VGG, and we are extracting specific feature maps. And what we are then doing is we are computing the perceptual loss function we are computing the perceptual loss by using the PL function, which works by summing the squared errors between all the pixels and then taking the mean. And the reason for doing this, again, as described by the authors, is that it preserves some extra level of detail while trying to reduce the amount of noise present in the image. And it focuses on like creating specific aesthetics such that like edges, corners, these things don't become too pixelated. Because if you do a pixel by pixel comparison, that may sometimes lead to those kind of issues happening. So that's the reason the perceptual loss function has been adopted by the authors of the paper, as well as the framework which we'll be using. And this is a sample super resolution example, as you can see, where this was the size of the original image. And once we increase the resolution, you can see larger dimensions, and most of the aesthetics of the image have been kind of similar, and it's not getting distorted too much. So let's dive into the hands-on. So this is the image super resolution notebook, and this is the framework, by the way, I'm using. For people who are interested, you can go to idealo/image super resolution on GitHub, and this has a nice framework where you can leverage a lot of already built models, and they have even trained this for like over, I think, 40 to maybe 100 epochs, and you can even use those pre-trained weights and directly use these models by just calling a specific weight parameter. We'll talk about this in the notebook also, but this is basically the framework I'm using. So the first thing is you can obviously check your GPU, whether that's working or not, because GANs are like notoriously slow to train. So you definitely need a GPU. You can install the ISR package by just doing a pip install ISR. And once that is done, what we need to do next is obviously we need to get some training data. So from where do we get this training data? This is where we typically get it. You can download these from the div2k repository, which is present. And these are the files. By the way, if you go to this website, you will see there are other resolution images also. Like this one is, every image is upscaled to twice its size. That is the high resolution version, but it even has versions where you can upscale it to 4 times the original low resolution size. So feel free to check it out if you're interested to do your own custom training, or if you have your own low resolution, high resolution images, you can even load that up. So as you can see, I download all this data, and it's pretty huge. As you can see, the high resolution images, you can see it's almost 3.3 gigs versus the low resolution version, which is like around 880 megabytes. So you get the point. The low resolution images are obviously going to take less space versus the high resolution ones. So once we download all these zip files, what we do is we have the training low resolution and the corresponding training high resolution files. And similarly, we have the data used for validation corresponding low and the high resolution images. So we download all of that, and then what we need to do is create our model architecture. So what are the models we will be using? Like I described before, we will be using the more enhanced residual dense network, which uses multiple RDBs with a skip connection or residual connections. So that is what we will be using here. And then we will be using a discriminator network for basically training, leveraging a GAN approach. And since we will be using perceptual loss typically to do the final computation, we will leverage the VGG19 model also to extract specific features from feature representations from the super resolution generated image and the target high resolution image. And there are other parameters also, like the layers to extract from the VGG, typically, which will be used in the perceptual loss, the patch size, where it basically looks at patches of image and it tries to resolve it to the high resolution version versus doing it one shot for the full image. And the other part is the upscaling factor, where we want to upscale it to 2 times the original image or 4 times and so on. So as you can see here, typically the scale I've taken is 2 times the original image. And if you remember, these are the parameters we covered earlier in our slide deck. So once you set these parameters with regard to the number of convolution blocks inside each residual dense block, the number of residual dense blocks, number of feature maps in the convolution layers, like as you can see here, we are using 64 and so on. Then what you do is you build your RRDN network. You build your VGG19 network. It's called cut VGG because we don't use the full network, obviously. We cut it to extract some specific feature maps. And the last part is basically the discriminator, which will help you in improving your training by where you generate your image and it tries to say whether it's like the high resolution image or not. So that is where we are using a combination of all of these models. And you can see that if you check the model summary, the layers are huge because it is using multiple residual dense blocks, as you can see. So, and this is our VGG network. As you can see, we are using only a part of it. We are not using the full VGG network. We'll dive into VGG 19 even in the next use case for style transfer. Now, the trainer object is where you need to initialize some of the key parameters, like when you are computing the loss, how much of a loss weight should you give to the generator, the feature extractor, and the discriminator, what kind of a loss you want to see on each of the specific models which are there. And as you know, the discriminator is all about saying whether an image is a matching image or not, whether it's a fake image or not. That is what the discriminator does for the GAN, if you remember, where the generator generates the image and the discriminator discriminates the image. So it is always a binary cross entropy because the output is always a 1 or a 0. And then there are other factors like learning rate and so on. And you can check out the details of the documentation here also to understand what are the key parameters being used in the trainer framework, trainer class. So in the ISR framework, the trainer class has a lot of things. So as you can see in the generator, we will typically give the generator model, which is basically the RRDN, the residual dense network model, which will help us in generating the images. We are also using a discriminator, which we had generated, let me not use the word generated, which we had constructed earlier, as you can see. So we also have a discriminator network. And we have the feature extractor network, which is the cut VGG19 model, which is used for computing the perceptual loss. And then we have the learning rate, the weights, and the data, and so on. And let's say you are you have trained for, let's say, 20 epochs, and you have saved the weights, and suddenly, let's say, you got disconnected or something happened. So how do you resume the training? You can just load up your previously saved weights, and you can continue the training. So this is basically the fine tuning, right? Where you don't again start from scratch. You pass in the weights of your previously trained models, and then you continue. And then we train the model here. So again, I have trained on Colab, and as you know, it takes quite a lot of time to train. So what I've done is I have trained for 10 epochs only. So obviously results may not be the best. Batch size of 8, and steps per epoch is 20. So that is what I've used. So in short, on an average, what is happening is like 100 plus or 120 odd images are being trained in every epoch. Like the low resolution gets converted to super resolution, and we compare with the high resolution and compute the loss. So I've trained for only 10 epochs. And as you can see, we are basically validating the loss over time and checking how it's performing. And once this is done, and basically it improves, the loss decreases over time, which means we are getting a better model, as you can see here. So val loss, it keeps decreasing over time, which means we are getting a better model across all the epochs. So what happens is once the model is trained for 10 epochs, we save the weights. So the trainer actually helps us in automatically saving the weights in the let me show you here in the weights directory. So as you can see here, the logs will be there in the logs directory, which you can visualize using a tensor board or something, and the weights get saved in the weights directory. So you can download these weights yourself. And now let's say you want to use this for inference or further training. What you do is you again create your generator network, because you don't need the discriminator anymore, because just remember, you were using that when you were training, where the discriminator was helping you improve the performance of your generator. But the generator is what helps you generate the LR image to the super resolution image or the high resolution image. So now once your generator is already trained, what you do is you construct the architecture of your RRDN in the same way in which you had done during your training time. So this is, by the way, a blank model with random weights. So if you use this directly, you will probably get junk. It will not even work. So now what you do is, this is a sample image, as you can see, in a low resolution, which we want to improve or upscale. So now what I do is this model which I had initialized, I load the weights which I had saved. By the way, as you can see, I had trained it for 10 epochs from the 0th epoch till the 9th epoch. So I load up the last weights of the model. And once I load this up, what I do is I also want to load some of the other models which Image Super Resolution provides to us. So these are the models which they have trained for more than 10 epochs. So I want to compare the performance, obviously, because 10 epochs will not really give me that good a performance. This was done just for the purpose of these kind of sessions. So this is where, as you can see, I initialize the models and I pass this argument, weights noise cancel, which was a special type of model which was trained, which kind of tries to smoothen some of the noisy artifacts which might come in the image once it's translated into a high resolution image, kind of a pixels or the blocky artifacts. And the other one is a standard RRDN network, which was trained using the GAN approach, basically the same approach which we just saw. So these models, they have trained for a lot of epochs, much more than only 10 epochs. So the idea is we have our model, which we have trained for 10 epochs. We have one of their models, which they have trained specifically for removing the noise canceling artifacts, and they have trained for a lot of epochs. We also have another model, which they have trained, the weights, which they have trained for a lot of epochs using this GAN approach. And the other approach we will use is a simple bilinear or a bicubic interpolation. Here we are using bilinear interpolation. So as you know, interpolation is one of the naive ways of increasing the size of an image. So that is what is will be our baseline. And then we will compare these three approaches, two with their weights and the last one with our weights of 10 epochs. So if you see here, this, by the way, I hope you can see, anyway, these are big images, so they cover most of the screen. But this is using the bilinear interpolation. And you can see here that these parts, if you see closely, it's kind of blurred. If you see the people also, it's kind of blurred. It's not as effective as you can see here, where you can actually see those brick structures in this architecture here. And you can even see these people clearly. And you can see that our model is this one, which was trained for only 10 epochs. And if you compare this with this, you see there is so much blurring around here. Let me see if I can zoom this. I hope it doesn't crash the screen. Yeah, I guess that's the maximum which can be gone. But the idea is basically, yeah, I guess this doesn't work unless I download this specifically. But the idea is basically we have this image, which is a naive version of a super resolution image with a lot of blurring artifacts. So if you download this yourself and you check it, you will get the idea of how it works. But if you see these images, like if you compare this with this, you see that it is a much clearer version. You see there is so much blurring here. But if you see this, you can see that this is a much clearer version, and it looks much more visually pleasing. So that is the power of super resolution. And I can show you another example here. So you see this is the standard image which we are trying to upscale. So now this you can compare. So you see here I have used the ESR GAN, the RRDN network, to generate this. And this is like 4 times the size of the original image. But you see there are some blocky artifacts here and there. So the noise reduction, the noise cancellation model, which they have trained, also helps in this. So if you see this, I'll hover over this. So you get the idea where it helps in removing some of those artifacts to an extent. So basically there are different modeling aspects here, which you can also check, where sometimes you may need to look at the fine features, but sometimes you may want to get a more smoothened image. So these help you in building these super resolution images versus just using a bilinear interpolation, which will give you kind of a blurred image and you can't focus on the finer aspects of the image. Similarly, this image is basically what I was talking about. This is a bilinear interpolation. But if you compare this with the noise cancellation one, you see that these parts are so blurred. But here we can see the snow is like, you can actually see it much more clearly. And you can see these features are much more enhanced. And this is the model which we trained after 10 epochs. So you can see there is still some redness which needs to go. But comparing with this image, we are definitely seeing much more finer particles of the snow on the leopard. And this gives you the idea of the power of these models, where if you train these GANs for longer and longer, you will get more visually pleasing results. Now, the last one is again a flower. I'll not go into this due to the interest of time, but let's dive into the next use case. So the next one is interesting. It's called as the neural style transfer methodology, where a lot of you may have used this app Prisma when it came out. And there are many more. I think, again, I'm not a guy who takes a lot of photos all the time, but I'm sure for the people who take it or who are enthusiasts, you may have used some of these apps where you can use what is known as these filters on the image to stylize the image and make it look kind of special and slightly different from how it would normally look like. So that is the whole premise of neural style transfer. So this is basically the idea, right? You have a base image known as a content image. You have a style image, which you want to transform on the content image. And this is the output you get, which is known as a stylized image. So what is neural style transfer? Based on the original paper from Gattis, you can check that out. Also, I'll share the name at the end of the presentation. But basically, it is a artificial or an algorithmically generated system, which is based on obviously a deep neural network, which helps in creating artistic images, which still retain the quality of the image. It is not like it gets completely distorted. And the idea is to use deep learning to compose or create or generate an image, which is our content image, in the style of the reference style image. And usually it uses neural network representations to separate and recombine the content and the style of these arbitrary images, where the whole aspect is to apply the style of the reference image onto the specific target content image, as you can see here, in this case, the Taj Mahal. And what we do is we are trying to apply this, I think this is from Van Gogh, very famous painting called the Starry Night, if I'm not mistaken. And the idea is to apply the style onto this image. And in the process, the original content of the target image should remain unchanged. So as you can see, we still see this and recognize that this is indeed the Taj Mahal. And the idea is it shouldn't get completely distorted. Like, it shouldn't change into this architecture. So you get the point, I hope, where the idea is we are basically stylizing our base content image. And as you can see here, what is the methodology for this neural style transfer? So at heart, so there is some really interesting math involved in this. And this is, I would advise everyone to actually do this as a side project if they get time, because if you really want to understand the math, like how is gradient descent, or how is linear algebra, or how do you work with tensors, and how are all of this useful in practical applications, I think there is no better application than neural style transfer, where it is not just about you loading up a, let's say, Keras model or a TensorFlow.keras model or a PyTorch model and just plugging it in. You actually need to go deeper into the math of this to understand about how do I represent the content of an image, how do I represent the style of an image, how do I combine both of them, how do I extract the style correlations from the base image. And that is where a lot of linear algebra, a lot of math is being used. Nothing to be worried about, because it is pretty straightforward, and I'm pretty sure almost every one of you will be able to understand. In case you don't, you can always reach out to me offline. I'll share my links later, but let's dive into it. So at heart, NST is an optimization technique, typo here, sorry for that, to take two images, basically a content image and a style image, also known as the reference style image, and to blend in together. Content is defined as the overall structure and high-level components of the image. Like, what is the structure of the image typically looking like? What are the high-level representations of the image, not the lower-level, finer representations? And style is basically those finer texture-based representations of the image, like what is the color, what kind of patterns are there in the image, what kind of textures are there in the image, and so on. And the idea is, like, the style or the reference image could be like a filter, an artwork, a painting. Typically, those are the ones which work the best. You could always use another image, but typically if it's kind of like a painting, as you can see here, or a sketch, it usually works better. A blended image should look like the content image, but it's like it should be painted in the style of the your style or reference image. And the idea here is we want to leverage a pre-trained CNN model. So here we'll be using a convolution neural network model, again, the VGG19, which we talked about during super resolution, to extract the style and the content representation so that we could generate a new image from the initial content image. So how do we do that? The idea is to use a pre-trained VGG19 model to extract these image representations. And as you know from your knowledge of convolution neural networks, and in case you haven't dived into it, a brief refresher here, the first few activations represent low-level filters like the edges, the textures, and so on. And the final few layers represent those higher level features like holistic features, eyes, nose, if you think about a facial recognition software. Intermediate layers are useful to define the representations of content and style, and that is what we'll look at shortly. Intermediate feature maps will be used to represent the content of the target image, and we will be extracting style feature representations from the style image, as you can see in this case. So we will be extracting like the color and the textures from this, but we need to convert that into what is known as the actual style of the image. So how do we extract the style from the representations of the style reference image? That is where we will be doing it using means and correlations across all the feature maps which are coming out from your intermediate conv layers, and we will discuss about this shortly. How do we actually do that? Some nice linear algebra goes into this process. And then obviously, like I said, it's an optimization problem. So what do you do there? You need to compute the content and the style representations from the base content image. This is the base content image and the reference style image. You need to extract the representations. And once you do that, what you need to do is you need to compute the content loss for the generated content image. So the base content image is this. You will extract the content representation of this image. You will then try to compute the content loss for once you generate a new version of the image based on this. You will want to compute the content loss for the generated content image. So this would be your final generated content image, but at every iteration, there will be one version of it. So you need to compute the content loss. You need to compute the style loss. So how do you get the style loss? You would again need to extract the style representations from this image. And from those style representations, you would need to get the style you can say the style features from that. So that is where we will get it using the means and correlation. And using that, you need to again compute the style loss. Then you need to regularize it. So if you don't regularize, what will happen is you will see a lot of, as we discussed earlier, those blocky or patchy artifacts, and those kind of pixelated artifacts we want to reduce. So that is kind of denoising, which we will do using something called the total variational loss. And then obviously the last steps is you compute the gradient of the loss and update your generated image using those gradients using the optimizer. So that's your standard neural network methodology with the backpropagation, where you apply the gradient back onto the generated image. So again, brief about CNNs. I think you all must be knowing about it, but the idea is it has a lot of different layers of convolution and pooling, and the idea is to extract the feature representations from some of these convolution layers. This is your image. A convolution layer is where you convolve a filter across the image using some strides. And the idea is once you get this is known as, by the way, a feature map. So once you get this feature map, which is computed from a convolution using this convolution filter across the image, translated across the image, you can do some max pooling or whatever, sum pooling, average pooling to downsample the image. These two, convolution layer and pooling layer, are the fundamental blocks of any CNN model, just a refresher for people. So we will be focusing, by the way, on the VGG19 model here, which is a 19-layer conv and fully connected deep learning model. As you can see, it has 16 convolution layers using 3x3 convolution filters. And we don't care about the fully connected layers here. This model was originally trained on the ImageNet database, as you know, part of the ImageNet challenge, where you have to predict 1,000 classes of images. So that's why the final layer is an output layer of 1,000 units, but we don't care about this. We will be using VGG19 as a feature extractor. So this is of our interest typically. So let's talk about these representations. Like I said, we will be using this VGG network architecture here to extract the style and the content representations. So Typically, a given input image is represented as a set of filtered images at each processing stage. So at every layer or at specific layers of the CNN model, we can use it to extract the relevant feature maps or feature representation. So based on the paper and based on also the official tutorial from TensorFlow 2, which I will link at the end of the slides, they have used the block 5 conv2 layer to extract the high level content of the image, also known as the content representation. What is block 5 conv2? So block 5 conv2 is going to be basically, I think, this one. Okay, so this is what is being used finally to extract the feature representations of the content image. And then you compute a mean square error of the content representation of, so remember, you always start with a base image, so you will compute the mean square error of from that base image with the generated image every time, right? And every iteration, the generated image, some components of the style will be imposed on it. So we will be using this to compute the content loss. Similarly, for style reconstructions, we use various blocks. We use block 1 conv1, block 2 conv1, 3 conv1, 4 1, 5 1 to extract style representations. These are like the style representations of the style reference image. And similarly, we compute the style loss by using a weighted style representation with the generated image every time, and we multiply it by a final style weight to get the style loss. We'll look at the equations of this shortly, where it will become more clear. So what is the content representation? This is like, as you can see, a standard feature map coming up from block 5 conv2. And you can see for that Taj Mahal image, we can see like how the content representation, how the neural network model is actually visualizing it. So from the base content image, we first extract the content representation using the block 5 conv2 layer. And the content loss is computed by comparing the content representation of this image, which we are generating, by the base content image representation. So this is, let's say, the base content image representation. We will compute the loss by comparing this with the same representation, which will come out from every time we generate a new image by infusing some style components. So as you can see, MSE of the original image, the content representation of the original image, this one. So content representation of the original image minus the content representation of your generated image with some infused style components at every iteration. You multiply it by the content weight, which is a weight we will also impose to say that we don't want to lose too much representation from the content image. So we have to put a weight for that. And we divide it by the number of content layers we are using. In this case, I think we are using 1. Similarly, style representation. So style representation, as you can see, this looks similar to that image earlier I showed from that paper, where we are extracting feature representations. As you can see from the base typo here, again, from the base style image, we extract the style representations using our pre-trained CNN. So from the base style image, we will extract the pre-trained representations for these 5 conv blocks. Then we need to compute the style of the image. As I said, you represent it using means and correlations across the representation. So how do you do it? This is where you use some linear algebra, where you construct what is called a gram matrix to get the representations, to get the style from those feature representations. So what is the gram matrix? It is a very simple concept. It is an average outer product of the feature vector with itself across all the locations. So the gram matrix is where you just do an outer product, so V transpose V, and you divide by the total number of locations, which is basically the length and the width of your tensors. And then you compute the style loss. As I said, you have a style image reference. So from your style image, you get the style components, and you subtract that from the generated image style representations, and you multiply it by some style weights. And the total variation loss, so as you can see, these were the original images. And if you do the style transfer, you end up seeing a lot of blocky artifacts. So how do you remove this kind of noise? So that is where we need to remove these high frequency artifacts, and that is where we use this total variation loss to penalize the high frequency components in an image. So the focus is to remove those edge components of the image and reduce the effect of noise due to these artifacts. And that is where total variation loss is used, which is the sum of the absolute differences for neighboring pixel values in the input images. And the last part is the optimization. So thanks to TensorFlow 2, you can use these constructs like gradient tape, which works in eager execution. I think a lot of people will be aware of this, those who use TensorFlow too. So what you do is you compute the content loss, style loss, and total variation loss. You sum them up to get the total loss at each iteration. You then update the image by applying the computed gradients. So you compute the gradients first, and then you apply the gradients on the image, basically. And you keep repeating this for a specific number of epochs. And this is a sample style transfer example, by the way, where we have, this is the original image of a building. This is a stylized image. It is a popular, I think, Prisma filter also. And as you see, with no total variation loss, we see there is a lot of noise in some places, but that is the thing which they try to kind of reduce and regularize when they apply the total variation loss. So let's go into the notebook. I will try to keep this not too long, considering the interest of time, but a lot of content is here. Let's dive into this. We first check our GPU here. We are using a 16 gigs memory GPU, and we just load up TensorFlow here. We have some standard image processing utilities to load up the image in the form of a TensorFlow tensor based on the path of the image. We restrict the maximum dimension to 512, by the way, for the image, just to so that it doesn't take forever to train. And then we load up the images. So this is our content image, and this is the style image. So now we want to apply the style transfer by infusing style elements from this image onto the content image. And that is where we first load up the VGG model. By the way, here I'm loading up the full model, as you can see. And then I'm just showing some predictions. So if I predict on this source image, it says that 99% probability is a mosque, which kind of makes sense based on the ImageNet labels on which it was trained on. But we need to use VGG as a feature extractor. So this time what we'll do is we load up VGG here, as you can see. And we are saying include top equals false. So what that means is we only load up the convolution architecture of the CNN model. We don't care about the fully connected or the dense layers, because we are not predicting. We are going to generate images by using this as a feature extractor. And these are the different blocks, block names, by the way, the convolution and the pooling blocks, as you can see. So you remember we will use some of these blocks to do the style transfer aspect of it, the style aspects, and we will use this block for the content representation. So block 5 conv2 is going to be our content layer representation, and for the style layer representations, we will use block 1 conv1, 2 conv1, 3 conv1, 4 conv1, 5 conv1, and so on. So these are some of the blocks which we will be using. And these are standard housekeeping operations of computing the length of the number of style layers and content layers. So now how do we extract the representations typically? So this is where we will leverage a VGG model here. We set the trainable to false because we only want to use it to extract representations, use it as a feature extractor, that's it. So we will be using this VGG model. We will not be training it. We don't care about training, so we set the trainable to false. And then what we do is we use this to get the list of intermediate output values based on the layer name which we pass, that, okay, get this layer for me. So this is what we do here. Now, let's say this is a style image. We can actually get the style representations by calling this function, saying that use the VGG19 model, use these style layers, and can you extract these layers for me? So if I use this VGG layers function from before, we can get all those layers. As you can see, I can actually look at each of these layers, look at the mean and the max pixels and so on. And this is how the feature representations look like, just like it was there on the slide deck. So you can see that these are the style representations which we're trying to extract from the style image using the neural network model. And now we need to compute style from the style representations. This is where the Graham matrix comes into perspective. So how do we do the Graham matrix computation? Let me go through this step by step so all of you understand this, because this is interesting. What we do is, let's look at, let's say, the first style layer. So block 1 conv1, let's say this is our style representation feature map, which we have extracted using VGG19 from the style image. So how do I get the style components of this? So what I do is, I will first just reshape the layer to get this. So you can see it's 410 cross 512, and there are 64 feature maps. I am just showing you the mean here, by the way. If you see here, I have just done a mean across all the 64 feature maps and shown you the mean representation. But remember, here the operations are happening on a tensor scale. So all the operations here are happening on a tensor scale. So we are actually going across all the 64 different representations of that feature map of size 410 cross 512. So what we do is we first get this feature map tensor. And then what we do is we want to translate this so that it becomes like, okay, we have 64 feature maps of 410 cross 512. So we just kind of shift it so that it becomes easier for us to do the matrix operations, which we will do next. So what we do next is we flatten the style representation tensor based on the batches. So as you can see, 64 cross, so 64 of feature maps are there, 64 cross, each feature map is of size 410 cross 512. What we do is we flatten each of them. So now we have a two-dimensional tensor of 64 feature maps, and each of them having a flattened vector of size 410 cross 512. So that is what we have. Now what we do next is we compute the Gram matrix, as I said, which is basically V into V transpose. It is an outer product. Remember, it's not a dot product which we are doing. So we are using the matrix multiplication operation from TensorFlow here. And as you can see, we are multiplying it by its transpose. So that is going to give us the Gram matrix. We extract the number of total locations. And this is where we get the total number of locations by just multiplying the shape, basically, of the rows and the columns in our tensor, which is going to be 209920, right? Which is the same as this one. And once we do that, we just have to divide our Gram matrix at every location using this. And this gives us a normalized Gram matrix. Okay, so this is what is known as the style representation from those feature representations which we are getting using those convolution blocks on the style image. So you can combine all of that into one big function here, and now you can use this function directly into your class which we'll build here. So we build a style content model class, and what we do here is we leverage the VGG19 preprocess function for all the style blocks, if you remember, right? So what we do here is we have the style layers and the content layers. What are the style and the content layers? Just let me scroll once again back for your convenience. So these are my style layers and the content layers. So what I'm doing is I'm basically extracting these feature representations using this class. That is all I'm doing here. And you can see that I get my content outputs, I get my style outputs, and for the style outputs, I need to obviously do a Gram matrix computation on the style output, right? I can't just use the feature representation directly versus in the content where I'm using it. So that is all I'm doing. And once I do that, this is how this you have already seen in the slide. This is how like some of the average representations of the Gram matrix looks like. This is again the block 5 conv2 representation of the content of the image, content representation. What we do next is it's an optimization problem. So we define an optimizer. Here we are using the Atom optimizer, as you can see here. And then once we have the Atom optimizer here, like I said, you need to use some weights to give special emphasis to the style and the content. So we don't want the style to completely overpower the image. So we are using a 0.01 style weight, and we are using a 10,000 content weight, 1E4. And we give separate weights to each of the conv layers also in the styles. And then we compute our style content loss function, which helps in, as you can see, the same thing which we discussed, where this is doing the mean square error by doing a style output minus the style target. So style target is the style representation of our initial reference style image, and style output is what we keep getting using our generated image. And as you can see, for the content image also, we do a mean square error here. So we do the same thing in both cases. We multiply by the weights and divide by the number of layers, and we sum up the loss to get the style and the content loss. And then we just train it using that same gradient tape operation I told earlier, where you do the extraction, you compute the loss, you compute the gradient of the loss, you apply the gradients and update the image, and you keep repeating this. So we repeat it for 10 epochs here. And once we run this is how the styled image looks like. So you get the point. And that is where you can see there is a lot of pixelation happening in many places. So can we reduce the noise in the image? And that is where we use what is called as the total variation loss, where these are the artifacts which we want to kind of reduce. And the total variation loss is basically, as you can see, we just sum up the deltas of the high pass XY function, where we are just looking at the neighboring pixels and we are trying to extract typically the edges, those noisy edges from here. So we are typically trying to extract that. And then we are just computing sum of that to get the loss. And that is exactly what we are doing here using the reduced sum of the deltas. So TensorFlow already has a total variation function. So you can see it's this, we get the same result as our manually generated function. So ultimately we'll be using this. And what we do here is we have the style content loss and we add the total variation loss also to it and assign some weightage to it so as to give some emphasis to the regularization. And again, we perform the same optimization. And as you can see now, some of those edges have kind of been denoised. And you can compare this also, as you can see here, with no total variation loss, and with total variation loss, you can see that it has kind of tried to denoise some of this. So now what you can do is you can combine whatever we have learned so far and build a huge pipeline by plugging in everything together into one function, as you can see. So what this does is it will get the input paths of your content image and the style image on the disk, and it will plug in everything we learned so far by computing the style loss, content loss, total variation loss, and optimizing the image and generating it. And if we pass in two images, basically, you can see that we get this. Now what we can do is we can try out other filters. Like this is a stylized sketch of the Gotham City architecture. And if we apply this on our Taj Mahal image, as you can see, a fair bit of noise here, which kind of gets reduced when we use the total variation loss. Similar examples, again, here we are using a wave portrait painting, and you can see how it looks like it's kind of underwater. So an interesting effect comes into play here. And then the next one is the famous character from Breaking Bad. A lot of you might know about him if you have watched the series. So here it kind of, as you can see, it makes it like similar to the style aspects here of black and white, and the vibrant colors have kind of they have gone here, as you can see. Similarly, applying a building with the style of the Starry Night painting, you can see how it looks like. Here, this is an example. And again, you can compare with different architectures. And as I said before, some of the noise, as you can see here, tries to get denoised here using regularization with total variation loss. Similarly, for the wave, as you can see, gives a kind of a feeling like this is underwater. And the last one is this Heisenberg filter. As you can see, it looks somewhat from one of those non-color kind of a noir movie cinematic, where it's lost all the vibrancy but retained the style of the image. So the last part I want to show you is the power of transfer learning again, where we have this TensorFlow hub, which is like a hub of different pre-trained models. And Magenta is an effort. You can check out the GitHub repository also. If you just Google TensorFlow Magenta, you can check out the repository where they have also published a paper of doing really fast image stylization. So what I've done here is I have loaded this model. So this model, by the way, is available on tfhub.dev. If you go here, you can even see details related to this model, right? Just to briefly show you. So you can even get updated versions of the model. As you can see, I've used an older version of the model. You can even experiment with the latest model, which I think was released a while back. So the idea is you will get a lot of things like the model weights, some examples of how to use the model, and so on. So TensorFlow Hub is a nice place. It's like a model zoo where you get different types of models for performing tasks like object recognition, segmentation, feature extraction, style transfer. And you can even upload your own models if you build something interesting, assuming it goes through the right review process. So we are using the weights of a previously built model. And what we are doing now is we have loaded up this model. Now we take in all our images again. And then what we do is we call this model, as you can see, the hub module is our preloaded model. And we pass in our content image and the style image. And that is all we need to do, just like the function we had created before. But as you can see, it trained and built like 8 images. It generated 8 images for me in only 416 milliseconds. But if you look at our trained models, it took a lot of time. Not like a whole lot of time, but still, this is much faster. So this is where you can leverage the power of these pre-trained models, and you can then see we get this nice model outputs where it's slightly different from our model because we have used a VGG19 model and manually trained it, but they have already pre-trained this model on a wide variety of image representations. And you can see some nice styles which have been applied to each of these images. So hopefully this gives you an idea about the power of generative deep transfer learning, where we looked at 2 use cases. One is where we upscaled an image, and we didn't lose the resolution aspects of the image, but we actually increased the resolution of the image. And the other part is where we generated new images again. And these images where we applied a style on top of a base content image, but we retained the content artifacts of the image. So this gives you an idea of like a image generation perspective towards deep transfer learning. Of course, there are many other use cases out there, image captioning and several others. I will be covering some of them in future sessions also, as well as if you're interested, you can check out one of my books on GitHub around transfer learning. I have open sourced the code also on GitHub. So let me just go back to the presentation briefly. So the research papers, again, I haven't invented any of this content. So thanks to all the researchers out there, you can check out all of these papers, by the way. If you just search super resolution, these are the top 3 papers which you will get: residual dense networks, enhanced super resolution using GANs, and photorealistic single image super resolution using GANs. And for style transfer, do check out these papers. A neural algorithm of artistic style, I think, is the classic paper on neural style transfer. So people who are interested, do check it out. And I hope you got to see the power of simple mathematical operations on building such a nice, powerful application. And as I said, image super resolution, do go to github.com/idealo image super resolution. They have a lot of nice models on super resolution, some of which we use today. And the style transfer tutorial, by the way, is not something which was built from scratch, though I have done it before when TensorFlow 1 was there using Keras in my book, but this one was built completely using TensorFlow 2. So a tutorial is also available here, but I have changed some of the things to adapt based on my intuition. Like the gram matrix, I have used my own intuition of using the core linear algebra operations versus some of the newer TensorFlow based functions like eigensum or einsum and so on. So do check it out. And last but not the least, these are my social links. Feel free to connect with me in case you have any follow-up questions. My transfer learning book content is there on github.com/Dipanshan S. Feel free to refer to it if needed. And hopefully the session was helpful. I think we are already much over time, but thanks a lot for attending, and thanks to TensorFlow user group and as well as Must Research for having me here.
Thank you very much, Dipanjan sir. It was indeed a very informative session. And also, I think every topic was very clear. So most of them don't have any doubts as of now,
Sure.
but we can give them some time so that they can ask questions.
Yeah, sure. In case of any questions, if you have some time, open to it. And otherwise, yes, definitely, you can always reach out to me offline. Absolutely.
So I don't think there are any questions as of now, sir. So I
Sounds
think
good.
yeah. So if you can make some time and read the comments later when the other people see after ending the broadcast, and you can clear their doubts.
Absolutely. And yeah, I do see some comments. Yeah, thanks a lot for all the appreciation. I really appreciate all of you spending time and spending your time here on a weekend. And yes, in case you, again, this content, by the way, is not like a mature content. That's why I haven't put it on GitHub yet. But in my GitHub, you will find a style transfer example. But in case you really want it, you can reach out to me. I'm working on some interesting aspects of transfer learning. So I will share more on that later on my LinkedIn also. And you will definitely get all these examples. Yep.
I see one question, sir. Can I pop it for you?
Go ahead.
So it is different in GAN and residual networks.
Okay, yeah, interesting question. So basically, GAN is generative adversarial networks, which has a generator and a discriminator. The idea is they work on what is known as the zero-sum game principle, where generator will keep trying to generate images and will try to fool the discriminator, whether it's a real or a fake image. And the discriminator's task is to see whether it's a real or a fake image. It will make that decision. That's why, remember, we talked about the binary cross entropy loss for discriminator. Residual networks are slightly different. The idea is, as we discussed, they have those skip connections. So ResNet is a very popular model which has those skip connections. So the idea is, often when you are having a multi-layered convolution network architecture, you sometimes lose some useful features along the way. So to reinforce that, you sometimes keep passing the upper convolution layer feature map activation output in the lower one. So that is where you have these skip connections, and that is the whole premise of residual networks. Do check out the ResNet model. That is the best place to start with learning about residual networks. Okay.
Okay, sir. Thank you. Would
Thanks
you
a
like
lot.
to answer just another question?
Mm-hmm.
I think how to reduce the neurons in an.
Reduce neurons in an artificial neural network. Again, there are various methods to this. You can check out ways to reduce the footprint of your deep learning models. There are things like student teacher enforcing called knowledge distillation. There is model quantization where you can reduce the weights and so on. So those are the things like knowledge distillation of neural networks. That is something which you should definitely look at, which can help you reduce the weights of your model also, and potentially some of those connections which are actually not being used at all in your deep learning model. So just search on reducing footprint of your deep learning model connections and you will come across these same concepts, and that should help you dive deeper into it. Yeah. Okay, feel free to reach out to me offline for more questions if needed. But yeah, thanks a lot. I don't want to again hold back everyone forever,
Yeah.
but thanks a lot for inviting me, and hopefully it was useful for everyone. Yep.
Yes, sir. Thank you. Thank you very much for your time, sir.
Absolutely.
Okay. So thank you to all the audience for patiently listening to us on a weekend, that too on a Saturday. That shows your enthusiasm towards data science and to learn new things. So I thank you all once again, and you can see the meetup links of all our groups, that is TFUG, GDG, and WIMLDS Mysore. You have all the meetup links, and that is being shared on the description of the YouTube video also. So you can feel free to join the meetup page, and also look forward for better and more informative sessions in the coming future. So thank you to each and every one of you for sparing time. Hope we will meet soon. So everyone, stay home, stay safe, and please do keep supporting us. Thank you very much.